In 2015, astronomers witnessed something so powerful it defied imagination, a single explosion in deep space that outshone entire galaxies. Named Assassin 15LH, it wasn't just the brightest supernova ever recorded, it was something far more mysterious. Its blinding light, strange behavior, and unexpected location challenged everything we thought we knew about how stars die. What caused this cosmic beacon? A collapsing star? A shredded sun? Or something entirely new? This is the story of the brightest, and most baffling, explosion the universe has ever revealed. But before we continue, subscribe to the channel so you don't miss out on any of these videos. What is Assassin 15LH? At first glance, Assassin 15LH seems like just another item on the long and growing list of cosmic explosions we call supernovae. But the truth is far more fascinating. The name Assassin 15LH stands for All-Sky Automated Survey for Supernovae, 2015, Object LH. It was the 338th supernova discovered that year, though calling it a supernova might not do justice to its power, peculiarity, and potential to rewrite scientific theory. Supernovae are among the most energetic events in the universe, occurring when stars reach the end of their lives. Normally, a massive star burns hydrogen into helium for millions or billions of years. When it runs out of fuel, its core collapses under its own gravity, triggering a violent explosion that can briefly outshine an entire galaxy. This is called a core collapse supernova. There's also another type known as a Type I supernova, which results from a white dwarf star pulling matter from a companion until it reaches a critical mass and detonates. These are extremely bright as well, used as standard candles for measuring cosmic distances. But then came superluminous supernovae, a rare and powerful subclass, at least 10 to 100 times brighter than a typical supernova. And standing above even those cosmic juggernauts was Assassin 15LH. This event was so luminous that its peak energy output exceeded 2 times 10 to the power of 45 ergs per second, a number that's hard to grasp unless you live in the realm of astrophysics. For perspective, our Sun outputs about 3.8 times 10 to the power of 33 ergs per second, which means Assassin 15LH was, at its peak, over 570 billion times brighter than our Sun. Not million. Not billion. 570 billion. That's like placing 570 billion suns into a single spot and flipping them on at once. It makes even other superluminous supernovae look dim. And yet this light came from an object so far away that it took almost 4 billion years to reach us. That means the explosion actually occurred long before our species even existed, before the dinosaurs, before Earth looked anything like it does now. What we saw in 2015 was a flash from the ancient universe, as if the cosmos had sent us a time capsule of brilliance. But here's where things started to get strange. Even though Assassin 15LH looked like a supernova, it behaved in ways no one had ever seen. Its light curve, which plots brightness over time, showed unusual features. Typically, a supernova will explode, reach peak brightness, and then slowly dim. But Assassin 15LH dimmed and then brightened again weeks later. This rebrightening phase was completely unexpected and did not align with any known models for how supernovae evolve. At first, scientists labeled it as a Type I superluminous supernova, which means a particularly bright supernova that lacks hydrogen in its spectral signature. But the more they examined it, the more inconsistencies appeared. For one thing, it occurred in a massive, passive galaxy, a galaxy that isn't actively forming stars. Superluminous supernovae, especially Type I, are thought to occur in young, star-forming galaxies, where massive stars still live and die. So what was a supposed massive star explosion doing in a dead galaxy? Even stranger was the absence of certain spectral features. Supernovae have light signatures that reveal their ingredients: hydrogen, helium, oxygen, and so on. But Assassin 15LH didn't quite match any known pattern. It almost looked like a supernova, but then again, not exactly. It was like finding a fossil that sort of looks like a dinosaur, but also kind of resembles a bird, and perhaps, something new altogether. One possibility raised was that this wasn't a supernova at all, but rather a tidal disruption event, TD, a different kind of cataclysm where a star wanders too close to a supermassive black hole and is torn apart by gravitational forces. These events can also be luminous, and some can reach near supernova brightness. But TDs also have unique light curves and spectral features, and again, Assassin 15LH didn't quite fit. In truth, Assassin 15LH sits at the crossroads of multiple astronomical mysteries. Its brightness is consistent with superluminous supernovae, but its behavior and environment don't match. Its spectrum defies typical classification, and its energy output doesn't align with any known theoretical model. It's as if the universe played a trick, disguising a completely new kind of object in clothing that mimics something we thought we understood. So what is Assassin 15LH? It could be the most extreme example of a known phenomenon, or it might be the first member of an entirely unknown class of cosmic events. That possibility alone makes it one of the most important discoveries in modern astrophysics. Events like this don't just add to our understanding, they shatter it. They force scientists to revisit long-held assumptions, update equations, and sometimes throw away old models entirely. In a universe already filled with mind-bending phenomena, black holes, neutron stars, gamma-ray bursts, Assassin 15LH has carved out a space of its own. It is not just the brightest supernova we've ever observed, it is the brightest mystery the universe has ever shown us. And with that, we now move to the moment that started it all, a night in June 2015, when astronomers caught the first glimpse of this extraordinary explosion. The story of Assassin 15LH begins not with a bang, but with a subtle change, a barely noticeable flicker in the sky, captured by the unblinking eye of a robotic telescope array constantly scanning the heavens for transients. It was June 14, 2015. Somewhere on Earth, life went on as usual. People awoke, drank their coffee, went to work, never suspecting that far above their heads, across billions of light-years of space, something had happened that would soon echo across the astrophysical world. That day, the All-Sky Automated Survey for Supernovae, or ASSN, pronounced Assassin, detected a new point of light in the sky, an object that hadn't been visible in previous images of the same patch of sky. Located in the southern hemisphere constellation of Indus, near the edge of a massive elliptical galaxy, this glowing dot was bright enough to be flagged immediately by ASSN's software. Now, ASSN is no ordinary telescope. It's a global network of small, robotic telescopes spread across multiple observatories, designed specifically to scan the entire visible sky every night in search of supernovae and other transient events. Unlike massive observatories that focus on small, deep slices of the sky, ASSN covers everything, again and again. Its job is to catch the unexpected, the sudden, the new, the unexplained. On that fateful day in 2015, the system's automated software noticed something unusual. A source of light had brightened dramatically in a location where no such object had been seen in previous nights. The brightness didn't just surpass normal stars, it leapt beyond what most known supernovae exhibit in their early stages. The system automatically flagged the object as a transient event, and that alert triggered a series of actions that would soon lead to a cascade of scientific interest. This is how ASSN works. Once a new light source is detected, the alert is verified, and the team behind the project jumps into action. Follow-up observations are conducted, usually within hours. They cross-check previous sky surveys like the Sloan Digital Sky Survey (SDSS), or Pan-STARRS to verify whether the object had been visible before or if it truly was new. In the case of Assassin 15LH, no such object had been recorded in that region. Whatever it was, it had suddenly appeared, and it was extraordinarily bright. Within days, follow-up spectroscopy, analyzing the light spectrum emitted by the object, confirmed that it was not a foreground star, nor a known galaxy, nor a quasar, but rather something entirely different. The initial data strongly suggested it was a supernova, albeit an exceptionally luminous one. But even that classification didn't sit quite right. It was immediately obvious to the ASSN team that this was no ordinary explosion. Here's what made the discovery so remarkable. ASUS SN is designed to catch supernovae early, within hours or days of their explosions. This gives astronomers the rare chance to observe them throughout their entire life cycle, from their initial rise in brightness to their eventual fade. So when Assassin 15LH was spotted, it was near the beginning of its energetic outburst. That early detection meant scientists could observe its entire evolution in detail. And it wasn't long before the numbers started rolling in and blowing minds. The peak absolute magnitude of Assassin 15LH was calculated to be about -23.5, making it more luminous than any other supernova in the recorded history of astronomy. In the language of brightness, where smaller or more negative numbers mean brighter light, -23.5 is extreme. That's more than twice as bright as the previous record holder. As news of the detection spread through the scientific community, observatories around the world began to mobilize. Within hours of confirming the object's existence, it became a target of intense observation by some of the most advanced instruments on Earth and in space. And this wasn't just because it was bright, it was because nothing else like it had ever been seen before. For comparison, Assassin 15LH was about 200 times more luminous than a typical Type I supernova and nearly twice as bright as the previous record holder for the most luminous supernova, SN 2006 GY. To say this caught the attention of astronomers would be a wild understatement. It was as if the sky had thrown them a curveball from across the universe, one wrapped in more questions than answers. But the initial detection also did something far more powerful. It set off a new era of curiosity and controversy. It was the kind of moment that defines a generation of research. Astronomers across the globe looked at the same data and came to wildly different conclusions. Was it a supernova, as first assumed? A black hole tearing apart a star? Or something we hadn't even imagined yet? It's important to note that in astronomy, discoveries don't come with trumpet blasts or grand announcements from the sky. They begin with cold data, a change in a pixel, a subtle rise in brightness, a signature in the spectrum. What matters is how quickly those signs are recognized for what they are, and how boldly scientists are willing to challenge the known in pursuit of the unknown. And that's what happened with Assassin 15LH. On June 14, 2015, an automated telescope noticed a dot in the darkness. But in that dot was encoded a cosmic message that the universe still holds secrets far beyond our comprehension. That even with all our tools, theories, and telescopes, we've only just scratched the surface of understanding what the cosmos is capable of. What started as a single alert from a robotic sky scanner would become the most luminous mystery in the known universe. And next, we'll meet the team responsible for spotting it, the astronomers behind the ASUS SN project who caught this event before it faded into the eternal void. In the vast theater of the cosmos, where cataclysmic events unfold across incomprehensible distances, few discoveries are ever made by accident. They are the result of quiet vigilance, years of planning, calibration, and the tireless labor of astronomers who rarely find themselves in the public eye. Such is the case with the discovery of Assassin 15LH. Behind that cryptic string of letters and numbers is a team of brilliant minds operating a cutting-edge robotic network built for one ambitious goal: to monitor the entire sky, every night, and catch the universe in the act of doing something extraordinary. That team is the All-Sky Automated Survey for Supernovae, known in shorthand as ASUS SN. Based primarily out of Ohio State University, ASUS SN was founded under the leadership of Professor Christoph Stanek, along with a team of astronomers that included Todd A. Thompson, Christopher Kohanek, and Benjamin Shapi, among others. These scientists envisioned a system that could close the observational gap in our sky surveys, an automated global eye that wouldn't just glance at the cosmos but watch it relentlessly, like a sentry standing guard at the edge of the unknown. At its core, ASUS SN is deceptively simple. It consists of multiple small aperture telescopes, each equipped with high-quality CCD cameras, placed strategically around the globe. These telescopes are not massive in size or cost like the Hubble Space Telescope or the Keck Observatory. But what they lack in individual might, they make up for in coverage, automation, and frequency. Most notably, They are designed to image the entire visible sky every 20 hours. That level of regularity is unprecedented in the world of transient astronomy. And it's that precise, nightly sweep that made the discovery of Assassin 15LH possible. As the OSIS-SN telescopes went through their routine observations in June 2015, one unit, located at Cerro Tololo Inter-American Observatory, CTIO, in Chile, noticed something new. A bright transient source had appeared near the edge of an otherwise quiet, passive galaxy. The system flagged it, and like clockwork, the team at Ohio State was notified. This seamless integration of hardware, software, and human insight is the very essence of what OSIS-SN was designed for. The software sifted through thousands of images, compared new data with archival observations, and quickly identified a candidate that stood out. Then the human element kicked in. Scientists scrutinized the coordinates, examined the light curve data, cross-referenced catalogs, and confirmed that the object was real, not an instrumental glitch, not a moving object like an asteroid, not a known variable star, but something far more intriguing. OSIS-SN had been detecting new supernovae since 2013, and by 2015, it had already found hundreds of them. In fact, one of its greatest strengths was its ability to detect bright, nearby supernovae early in their evolution, making it an invaluable tool for follow-up observations by larger observatories. But nothing the team had seen before came close to what they had just uncovered in Assassin 15LH. This was not merely another data point. It was a cosmic outlier, a beacon that burned brighter than anything they had catalogued, and brighter than anything anyone had catalogued. Soon after the initial detection, Benjamin Shapi, then at the Carnegie Observatories, played a key role in analyzing the early data and initiating the follow-up efforts. The team quickly submitted their findings to the Astronomers Telegram, a public alert service for significant astronomical events, and within days, the world's scientific community had its eyes turned toward this enigmatic light in the Indus constellation. But what made OSIS-SN's discovery so exceptional wasn't just its novelty. It was the way it was found. Unlike many discoveries made by accident, or those requiring human operators to be observing the right patch of sky at the right time, this one was purely systematic. It was algorithm-driven discovery, a triumph of 21st-century astronomy where automation meets intuition. It proved that science doesn't always require massive billion-dollar facilities to make groundbreaking discoveries. Sometimes it just takes an intelligently designed network and a dedicated team who knows how to listen when the cosmos speaks. And indeed, OSIS-SN listened well. Their mission had always been to catch supernovae in real time, to provide alerts early enough that others could follow up before the brilliance faded. Assassin 15LH was exactly the kind of event they were built to discover, but on a scale no one anticipated. In fact, it wasn't until the peak brightness measurements came in that the team realized they had found something unprecedented in the history of astrophysics. Not just a supernova. Not just a record breaker. But an event that didn't quite fit any known category. The legacy of this discovery doesn't rest only in the brightness of the explosion. It lies in what it revealed about how far we've come in our observational capabilities. With robotic telescopes stationed strategically around the globe, programmed to continuously scan the sky and recognize anomalies within hours, we've entered an era where the universe can no longer hide its most spectacular events in the shadows. And the team behind OSIS-SN knew this. They understood that their work wasn't just about taking pictures of the sky, it was about monitoring the pulse of the cosmos. Like doctors with a stethoscope pressed to the chest of the universe, they listened for the rhythm of stars, the sudden silence of collapses, and the brilliant heartbeats of explosions. Assassin 15LH was one such heartbeat, a thunderous, radiant pulse unlike anything ever recorded. But what came next would be even more remarkable. Because when the data started pouring in, astronomers around the world would find themselves caught in a whirlwind of confusion and disbelief. Assassin 15LH didn't behave the way a normal supernova should. It was as though the universe had handed us a jigsaw puzzle, but the pieces didn't quite fit. And so we arrive at the next chapter in this mystery, where awe turned into uncertainty. What was this thing really? And how could something so brilliant be so baffling? In the immediate aftermath of Assassin 15LH's discovery, a strange and unsettling feeling began to settle over the astrophysical community, a mix of awe, curiosity, and more than anything, confusion. The ASSN team had done their job flawlessly. They had identified, tracked, and confirmed a transient object with unmatched luminosity. But now came the harder part, explaining what it actually was. And it wasn't going to be easy. At first, everything pointed toward the classification that gave the event its name, a supernova. But not just any supernova. Assassin 15LH appeared to be a Type 1 superluminous supernova, SLSNI, a rare subclass of cosmic explosions that defy normal luminosity expectations. Even within this already extreme category, however, Assassin 15LH was clearly something else. Its brightness wasn't just impressive, it was unprecedented. It was so luminous that it didn't merely stretch the limits of known physics, it broke them. To grasp the scale of this confusion, one must understand the rough boundaries within which most supernovae operate. A typical supernova releases around 10 to the power of 44 joules of energy, and reaches a peak brightness of around -19 to -21 absolute magnitude, which is bright enough to outshine entire galaxies for a brief time. Superluminous supernovae go a bit further, sometimes achieving an absolute magnitude of -22 or even -23 in extreme cases. But Assassin 15LH clocked in at an absolute magnitude of -23.5, translating to a luminosity of roughly 2.2 times 10 to the power of 45 erg/s at its peak. That's about 570 billion times the brightness of our Sun, a staggering figure, almost twice as luminous as the previous record holder. This sheer intensity baffled scientists. No known mechanism comfortably accounted for such an energy output. If this were a traditional SLSNI, the explosion would have required an energy reservoir orders of magnitude beyond anything previously observed. And herein lay the core of the confusion. Our current models didn't allow for this kind of event. Assassin 15LH was not just an outlier. It was, for lack of a better term, an anomaly, a data point that pointed to a physical phenomenon no one had anticipated. Initially, many leading experts assumed it was an extreme but still explainable member of the superluminous family. It shared some of the spectral features associated with SLSNI explosions, such as the absence of hydrogen in its spectrum and the overall behavior of its light curve. But even these similarities began to break down under close examination. The light spectrum lacked the kind of emission lines typically associated with known supernova elements, and the time scale over which the brightness decay didn't quite match any established patterns. As data from observatories around the globe poured in, especially from facilities like SWIFT, Pan-STARRS, and later, the Hubble Space Telescope, astronomers began to see that this wasn't a straightforward case of supernova, but brighter. It was something else entirely. The temperature of the object remained anomalously high for far longer than expected. Its light curve initially followed a rapid rise and gradual decay, similar to a superluminous supernova, but then, defying all expectations, brightened again. This dip and rebrightening phenomenon was extremely rare and difficult to explain within the standard supernova framework. The confusion deepened when theoretical astrophysicists began crunching the numbers. To sustain such a luminous output, the object would have required an incredibly powerful energy source, far greater than any known radioactive decay process could provide. The decay of nickel-56, the typical energy source behind supernovae, simply couldn't explain it. Even under the most optimistic assumptions, a radioactive decay model would have needed several solar masses of nickel-56, an amount that bordered on the physically impossible. Then came the discussions around magnetars, a kind of hypermagnetized neutron star with an extraordinarily fast spin. Magnetars have been proposed as potential power sources for some of the most energetic SLSNA. But even the most optimistic magnetar model couldn't easily explain Assassin 15LH. The necessary conditions would have required an initial spin period of less than a millisecond, combined with an extremely strong magnetic field on the order of 10^14, 10^15 Gauss. This placed it right on the edge of theoretical feasibility, and even then, it couldn't quite match the observed energy budget or the light curve behavior. At the same time, the host galaxy, a quiet, massive elliptical galaxy with low star formation, didn't match the usual environments where SLSna are found. Typically, SLSna occur in dwarf galaxies with high star formation rates, where massive, short-lived stars can go supernova within a few million years of formation. Yet Assassin 15 LH came from a galaxy where very few stars are being born, suggesting the explosion didn't arise from a young, massive progenitor star, the kind expected to produce a superluminous supernova. This mismatch between the event and its environment only served to deepen the mystery. It was like finding a volcano erupting in the middle of an icy desert, technically possible under some rare geological conditions, but definitely not where you'd expect to find one. The theoretical tug-of-war that followed was intense. Some researchers dug deeper into existing models, stretching them to accommodate Assassin 15 LH's abnormality. Others suggested it might be an entirely new class of explosion, unrelated to known supernova mechanisms. A few even questioned whether the event was real in the traditional sense. Perhaps it was some new kind of lensing artifact, a fluke in the detection software, or an unknown observational error. But repeated confirmations from multiple instruments across different wavelengths dismissed those notions quickly. By the end of 2015, the scientific papers began to pile up. Astrophysicists were scrambling to make sense of the data. Some tried to frame Assassin 15 LH as a hybrid event, part supernova, part tidal disruption event, more on that possibility later. Others leaned heavily on modified Magnetar models, invoking extreme and perhaps unrealistic parameters to make the math work. Still others proposed that it was a massive star collapse near a black hole, resulting in some form of relativistic jet-driven outburst that we hadn't fully theorized before. But all of these interpretations came with caveats, large ones. There was no single explanation that satisfied all the observational constraints. Each theory accounted for some aspects of the phenomenon but failed to explain others. And this is what made Assassin 15 LH truly revolutionary. It exposed the limits of our understanding. It wasn't just that we didn't know what it was that every framework we had crumbled under its light. This kind of confusion is rare but not unprecedented in science. Throughout history, the most paradigm-shifting discoveries have often begun with anomalies, events that don't fit the mold and force us to rethink the mold itself. Assassin 15 LH became one of those moments. It didn't just shine brighter than any other supernova. It also cast a light on the gaps in our knowledge, revealing how much we still don't understand about the violent deaths of stars and the extreme physics of the universe. Astronomers love a good mystery. But Assassin 15 LH didn't just present a mystery, it demanded an answer, and then cruelly refused to give one. Every model proposed seemed to run into a wall. Every explanation required extraordinary conditions or speculative physics. The object became a scientific paradox, a challenge to theorists, an obsession for modelers, and a sobering reminder to all astronomers. The universe always has surprises waiting in the dark. As the debates raged on, more and more attention was paid to the exact nature of its brightness. Could we really quantify just how luminous this event was? And if so, could that number provide the key to unlocking its origin? That question would be the next frontier, understanding how bright was Assassin 15 LH, really, and whether that brightness held the secret to what made it so incomprehensibly powerful. To truly grasp the magnitude of Assassin 15 LH, we have to step far outside the comfortable bounds of everyday understanding. Numbers are often thrown around in astronomy with such magnitude that they risk becoming meaningless. Millions of light years, billions of stars, trillions of planets. But even in this field of extremes, Assassin 15 LH forced scientists to invent new metaphors just to describe its brightness. At its peak, this cosmic explosion emitted light with an intensity nearly 570 billion times brighter than the Sun. To call that dazzling would be an understatement. It was, quite literally, record-shattering. Let's break this down. The Sun has a luminosity of about 3.828 times 10 superscript 2 watts, or 382.8 septillion watts, a figure already unfathomable in human terms. Now multiply that number by 570 billion. You get a value exceeding 2.18 times 10 superscript 3 watts. This means that for every single second Assassin 15LH was at its brightest, it was releasing more energy than our entire sun emits over tens of thousands of years. And that's just invisible light. When you include energy across the electromagnetic spectrum, ultraviolet, infrared, and possibly high-energy X-rays, the total energy output may have been even greater. In terms of absolute magnitude, a scale astronomers use to compare the intrinsic brightness of celestial objects regardless of distance, Assassin 15LH was measured at -23.5 at peak brightness. To put this into perspective, the lower the number, the brighter the object. A standard supernova might reach about -19 to -20. The full moon seen from Earth is about -12.6. Venus shines at about -4.9. And the brightest star in our night sky, Sirius, has a magnitude of -1.46. Assassin 15LH outshone entire galaxies, each containing hundreds of billions of stars, with just a single point of light. And even though it was located 3.8 billion light-years away, it was so bright that ground-based telescopes detected it clearly, as if it were a nearby galaxy lighting up in one explosive breath. Remember, light takes time to travel. The light from Assassin 15LH we saw in 2015 had been traveling across the universe since before humans existed as a species. And yet when it arrived, it was bright enough to stand out against the deep tapestry of space, as if it had only just happened next door. That's not just impressive, it's cosmically humbling. The enormous luminosity of Assassin 15LH is not just a curious fact, it's a central mystery. When astronomers encounter an object with such brilliance, the immediate question is, what power source could possibly generate that much energy? Ordinary supernovae are powered by the collapse of a massive star's core, followed by a violent expulsion of its outer layers. In most cases, the explosion is driven by a mix of neutrino outflow and radioactive decay, particularly from unstable elements like nickel-56, which decays into cobalt and then iron, releasing energy along the way. But this standard mechanism hits a wall when you try to explain Assassin 15LH. To generate the kind of luminosity it displayed, it would need to synthesize tens of solar masses of nickel-56 during the explosion. But astrophysical models don't support this. Theoretically, the upper limit of nickel-56 that can be produced even in the most energetic supernovae is just a few solar masses at best. Assassin 15LH would need at least 30, probably more, pushing it outside the realm of known stellar nucleosynthesis. This led to one of the most fascinating scientific debates surrounding the event. Was Assassin 15LH a supernova with an unprecedented explosion mechanism, or was it something else entirely? Could some other form of energy, like a central engine, such as a spinning neutron star or a rapidly accreting black hole, be behind the glow? Let's explore that in terms of energy density. For an explosion to produce light on that scale, it must not only be energetically intense, but it also has to be incredibly efficient at converting internal energy into radiation. Most supernovae radiate only a fraction of their total kinetic energy as visible light. The rest goes into neutrinos, kinetic shockwaves, and heating of surrounding gas. But Assassin 15LH was different. Its radiative efficiency had to be off the charts, suggesting not only a massive reservoir of energy, but a mechanism that channeled it into visible wavelengths far better than any supernova we'd seen before. There was also the problem of how long the brightness lasted. Assassin 15LH didn't just flare and fade quickly. Its high luminosity persisted for months, which meant the central engine, whatever it was, continued to pump energy into the expanding shell of ejecta long after the initial explosion. This ruled out simple flash-in-the-pan models like some forms of collapsars, collapsing stars, or gamma-ray bursts. Something had to be sustaining the light. The slow decline of the light curve was just as telling as the peak itself. Instead of following the relatively predictable decline seen in normal Type 1 or Type 2 supernovae, Assassin 15LH exhibited a gradual dimming, followed by an unexpected rebrightening several weeks later, a rare and puzzling feature. This would indicate either a re-energization of the explosion, perhaps via interaction with circumstellar material, or a delayed release of energy from a central engine. Neither was a clean fit with existing models, and both implied extreme astrophysical processes. To add another layer, astronomers compared Assassin 15LH with other superluminous events. One of the most famous before this was SN 2006 GY, which reached around -22 magnitude and was previously considered one of the brightest ever seen. Another was SN 2010 GX, a fast-evolving Type 1 SLSN. But both paled in comparison, not just in brightness, but in behavior and duration. Assassin 15LH wasn't just more luminous, it was substantially more complex. This level of luminosity also forced astronomers to wonder about its impact on its host galaxy. Could an explosion this bright affect star formation in its local environment? Could it irradiate nearby gas clouds or even strip atmospheres from orbiting exoplanets, if any existed in proximity? The implications of such energy being released all at once, even in a distant galaxy, hint at the raw destructive power of cosmic phenomena on galactic scales. So why does it matter how bright Assassin 15LH was? Because brightness is the currency of cosmic diagnostics. It's how we calculate distances, determine energies, measure time scales, and probe the mechanisms behind explosions. In this case, brightness was both the key and the lock. It told us that something spectacular had occurred, but it also prevented us from fitting that spectacle into any known box. It was like hearing a sound so loud that your instruments couldn't measure it, and then realizing your very definition of sound needed to be revised. The brightness of Assassin 15LH wasn't just impressive, it was disturbing, in the best scientific sense. It made experts question the limits of star formation, black hole physics, and even the life cycle of galaxies. It demanded answers from a field that thought it had already catalogued the worst the universe could throw at it. And perhaps the most haunting question of all was this: if Assassin 15LH could shine that brightly from 3.8 billion light-years away, what would happen if such an event occurred in our own galactic neighborhood? What would the sky look like? What effects would we experience? Would we even survive the onslaught of radiation? These questions, and their chilling implications, begin to open up another dimension of the story. But before we explore those hypotheticals, we must first return to the reality of Assassin 15LH's location. Where exactly did this cosmic juggernaut take place, and what does that tell us? To fully appreciate just how extraordinary Assassin 15LH is, it helps to compare it directly with the other giants of the cosmic stage, those rare and violent supernovae that have left their mark on astronomical history. Even among these awe-inspiring celestial events, Assassin 15LH stands out as an unmatched anomaly, a staggering outlier that defies traditional understanding. Let's begin with SN 2005 AP, which for many years held the title of the most luminous supernova ever observed. Discovered in 2005, it reached an absolute magnitude of around -22.7, making it about 400 billion times more luminous than the Sun. This explosion was already hard for scientists to explain using standard models. Many suspected it might belong to a class known as superluminous supernovae, SLSNA, particularly the hydrogen-poor Type 1 SLSNA, believed to be powered either by massive quantities of radioactive nickel or by a central Magnetar engine. But even SN 2005 AP now seems tame in comparison. Assassin 15LH outshone it by nearly a factor of 2, reaching a peak absolute magnitude of -23.5 and an estimated brightness of 570 billion times that of our Sun. Then there was SN 2006 GY, which reached about -22 in magnitude and was considered one of the most energetic supernovae ever observed in terms of total energy output. It was classified as a Type I supernova, rich in hydrogen and thought to be the explosive death of a very massive star, possibly a luminous blue variable like Eta Carinae, that underwent violent mass loss episodes before the final detonation. SN 2006 GY was notable for the interaction between its ejecta and dense circumstellar material, which prolonged its brightness and caused a drawn-out peak that lasted for weeks. But even this dramatic light show paled next to Assassin 15LH. Not only was Assassin 15LH brighter, it was more puzzling, showing none of the telltale hydrogen lines expected from such interactions. Another notable comparison is SN 2010GX, which was one of the earliest and best-studied hydrogen-poor superluminous supernovae. It reached a peak magnitude of about -21.2 and displayed a fast rise and relatively fast decline in brightness, suggesting a powerful explosion with minimal circumstellar interaction. While it provided valuable insight into the early light curve behavior of SLS-9, its power and longevity were still significantly overshadowed by Assassin 15LH. And consider SN 2003 Ma, discovered in 2003 and recorded in the Magellanic Clouds. This event, though not as bright and visible light as Assassin 15LH, released a staggering total energy output of over 4 times 10 superscript 1 ergs, making it one of the most energetic events ever seen. But again, it maintained that luminosity over a longer duration rather than achieving a peak intensity comparable to Assassin 15LH. It was like comparing a steady bonfire to a thermonuclear flash, impressive in its own way, but not the same league in terms of brilliance per second. When we turn our gaze to gamma-ray bursts, GRBs, often considered the most energetic events in the universe, things get even more interesting. GRBs like GRB 080319b, nicknamed the Naked Eye Burst, release brief but intense flashes of energy, some even visible to the unaided eye despite being billions of light-years away. These bursts can momentarily outshine entire galaxies in gamma rays, but their optical counterparts fade quickly, within seconds to minutes. Assassin 15LH, on the other hand, stayed luminous in optical wavelengths for months. It wasn't a flash, it was a burning beacon that refused to die. This duration is key. Unlike GRBs or even many SLSNA, Assassin 15LH exhibited a plateau-like behavior in its light curve, with a slow decline followed by an unexpected resurgence of brightness. This extended display not only allowed astronomers to observe it in detail, but also suggested that whatever mechanism was powering the event wasn't a one-off release of energy. It was something sustained, something continuously feeding the explosion for weeks on end. Even parent stability supernovae, which result from the deaths of extremely massive stars, above 100 solar masses, couldn't match the output of Assassin 15LH. These are considered among the most powerful thermonuclear explosions possible, but none recorded so far have approached the brightness of this supernova. In theory, a parent stability event could produce huge amounts of radioactive nickel, but even the upper models of such explosions don't account for the kind of brightness Assassin 15LH reached. Then there's SN 2016 APS, an ultra-energetic supernova detected after Assassin 15LH, which briefly rivaled it in terms of total output and was estimated to be powered by a massive core collapse explosion. It released about 5 times 10 superscript 2 ergs of energy, comparable in some ways to Assassin 15LH. However, even in that case, the light curve and spectral features fit within expected models for extreme stellar explosions. Assassin 15LH still managed to remain a square peg in a round hole, brighter, longer lasting, and more mystifying. So why is this comparison important? Because each time astronomers thought they had found the limits of nature's brilliance, Assassin 15LH raised the bar. It wasn't just another superluminous supernova. It was something unprecedented, an event so luminous that it challenged the definition of what a supernova even is. Its unmatched brightness, duration, and spectral peculiarities set it apart from all other known stellar explosions, placing it in a category of its own. And in astronomy, such outliers are precious. They are the anomalies that force us to revise our models, rethink our assumptions, and explore new physics. Assassin 15LH didn't just break records, it shattered them so thoroughly that astronomers were left wondering whether they had witnessed a completely new type of astrophysical event. One scientist famously remarked that Assassin 15LH was not merely a brighter supernova, it was a completely different beast. This was more than metaphor. It was a recognition that the object might not be a supernova at all, at least not in the traditional sense. Its light, its spectra, its host galaxy, all hinted at something that didn't quite belong anywhere we expected. And so, with Assassin 15LH now standing head and shoulders above every known cosmic explosion in terms of peak luminosity, the next logical question was, where exactly did this occur? And what kind of environment could produce, or even survive, such an event? To begin unraveling the mystery of Assassin 15LH, we must look deep into the cosmos, billions of light years from Earth, where this extraordinary event took place. The location of Assassin 15LH in the vast expanse of the universe is more than just a coordinate. It's a clue, perhaps one of the most important ones, in the ongoing effort to understand what it truly is. Assassin 15LH occurred approximately 3.8 billion light-years away from Earth, a staggering distance that places it well outside our local galactic neighborhood, in the depths of the observable universe. To give this context, when light from Assassin 15LH began its journey toward Earth, complex life was just beginning to evolve on our planet. Entire epochs have passed since that light first set off, carrying with it the story of a cosmic catastrophe that astronomers would only witness eons later in 2015. But location in the universe isn't just about distance, it's also about context. The environment in which a supernova occurs can reveal an enormous amount about the nature of the explosion. For a typical core collapse supernovae, the kind that result from the death of massive stars, we expect to find them in star-forming regions, within blue, irregular galaxies where hot, young, short-lived stars dominate. These environments are bustling with stellar birth and death, a cosmic cycle that regularly produces such explosive events. That's what made Assassin 15LH's location so puzzling. This cosmic event didn't take place in a high-energy, star-forming galaxy as one might expect for a superluminous supernova. Instead, it erupted in a massive, quiescent, red galaxy, a type of galaxy more commonly associated with old stellar populations, where star formation has long ceased. These galaxies, often elliptical in shape, are sometimes referred to as red and dead galaxies because they are largely populated by older, low-mass stars and show little to no evidence of recent stellar activity. In fact, the host galaxy of Assassin 15LH is quite unlike any other associated with previously observed superluminous supernovae. This galaxy has a high stellar mass, more than 100 billion times the mass of the Sun, and crucially, shows no clear signs of ongoing star formation. That simple detail throws a major wrench into the assumptions astronomers had been working with. After all, superluminous supernovae are typically linked to the deaths of massive, short-lived stars that burn bright and die young, usually in galaxies that are actively creating new stars. Yet Assassin 15LH didn't get the memo. It exploded in an environment where such massive stars shouldn't exist anymore. This led to serious doubts about whether the event could even be a supernova at all. Because if it wasn't powered by the collapse of a massive star, what else could have produced such unprecedented energy? Adding to the mystery was the fact that the position of the explosion was incredibly close to the center of the host galaxy. Observations from the Hubble Space Telescope and other instruments placed Assassin 15LH within just a few hundred light-years of the galactic nucleus, a remarkably precise location for a transient event. This central positioning is highly unusual for a supernova, which can occur at various places throughout a galaxy. However, it is consistent with other types of extreme cosmic phenomena, particularly those involving supermassive black holes, which are known to reside in galactic centers. This raised a compelling possibility. Could Assassin 15LH have originated not from a dying star, but from a black hole interacting with a star near the galactic core? The idea began to gain traction, especially when astronomers realized that the host galaxy was not like the typical homes of Type 1 superluminous supernovae, but was more reminiscent of the host environments of tidal disruption events, TDEs. In TDEs, a star wanders too close to a supermassive black hole and is torn apart by the intense tidal forces. The resulting debris can produce an outburst of light that rivals or exceeds the brightness of a typical supernova, especially when viewed across multiple wavelengths. Yet the location alone couldn't confirm this alternative theory. TDEs tend to show particular signatures in their light curves and spectral data, some of which were absent or ambiguous in Assassin 15LH. So, while its position in the heart of a massive galaxy suggested a black hole could be involved, the other aspects of its behavior didn't fit cleanly into that box either. It was, yet again, a cosmic contradiction. Still, the precise placement of Assassin 15LH in the galactic nucleus made it impossible to ignore the possibility of central engine-powered phenomena. Some astronomers hypothesized that if this was indeed a supernova, it might be one of a new class, centralized, ultra-energetic explosions whose energy source could be tied directly to the dynamics of the supermassive black hole at the core. Others speculated that we may have witnessed a rare alignment, where the explosion occurred so close to the core that it gave the illusion of being nuclear, though it was actually offset. But even the best alignment scenarios couldn't quite explain away the clear observational data. Assassin 15LH occurred very close to the galactic center, possibly too close to be coincidence. Moreover, deep ultraviolet imaging by Hubble showed no sign of star-forming regions near the explosion site, ruling out the possibility that this was a patch of newly ignited star birth hidden from earlier instruments. The galaxy itself, though massive and mature, did not seem to be harboring the type of environment typically needed to produce massive stars capable of going supernova in the first place. In other words, the where of Assassin 15LH only deepened the mystery. It was like finding a lightning strike in a desert where there should be no clouds. Everything about its location contradicted expectations: its distance, its proximity to the galactic core, and especially the kind of galaxy it called home. It's worth noting that this is not the only time a transient event has challenged our expectations about host environments. Astronomers have long known that nature can be unpredictable, and rare phenomena sometimes defy the trends seen in more common events. But Assassin 15LH wasn't just rare, it was unique. The brightest, most powerful supernova-like explosion ever observed occurred in the least likely type of galaxy, in a place where nothing of its kind should happen. And yet it did. And so, the puzzle pieces continued to shift. If this was a supernova, it was unlike any ever seen. If it was a tidal disruption event, it didn't behave like the others we know. And if it was something else entirely, something new, something unclassified, then its location in the cosmos might be the very key to unlocking its identity. As astronomers dug deeper into the behavior of Assassin 15LH, they began analyzing its light curve, the graph that tracks its brightness over time. And what they found next would throw yet another wrench into the traditional narrative, adding one more layer to the most enigmatic explosion the universe has ever shown us. In the cosmic realm of cataclysmic explosions, superluminous supernovae, SLSNA, stand as some of the most powerful and rare events ever observed. These are not your average stellar deaths. Traditional supernovae already unleash staggering amounts of energy, but superluminous supernovae take that to another level, shining 10 to 100 times brighter than typical Type I or core collapse supernovae. For years, SLSNA have fascinated astronomers because they challenge the boundaries of known physics and force us to reconsider what stars are capable of at the end of their lives. When Assassin 15LH was first discovered, it was quickly labeled as a Type I superluminous supernova, but almost nothing about it fit neatly into that category. To understand the gravity of that classification, and its limitations, we need to explore what defines a superluminous supernova in the first place. SLSNA are typically divided into two major types: Type I, SLSNI, and Type II, SLSN2. The primary difference lies in whether or not hydrogen is present in the spectra of the explosion. SLSNI events lack hydrogen, indicating that the progenitor star had already shed its outer hydrogen layers before it exploded, while SLSN2 events display hydrogen signatures, suggesting they occurred in massive stars that retained their outer layers. SLSNI explosions are generally believed to originate from massive stars, perhaps 20 to 50 times the mass of the Sun, that undergo extreme core collapse events. These explosions are typically thought to be powered by a central engine, such as a newly formed Magnetar, a rapidly rotating, highly magnetized neutron star that injects energy into the expanding supernova ejecta, making the event more luminous and longer lasting than normal supernovae. SLSNI events have certain spectral characteristics, including broad absorption lines, blue continua, and no hydrogen features. Assassin 15LH, at first glance, seemed to match some of those traits. Its early spectra were notably hydrogen-poor, and the peak luminosity suggested it was more than twice as luminous as any supernova ever recorded. This led to its initial classification as a Type 1 superluminous supernova. But almost immediately, astronomers noticed discrepancies, subtle at first, then glaring. The first red flag was the light curve behavior. Superluminous supernovae tend to have predictable rise and decline patterns in their brightness over time. Assassin 15LH did not follow this script. Its initial rise to peak brightness was consistent with SLSNI behavior, but after the expected decline began, something strange happened. The brightness dipped slightly, then rose again weeks later. This kind of rebrightening is highly unusual in known SLSNI events. In fact, it's almost unheard of. The cause of this secondary bump remains hotly debated, with no clear explanation in the context of existing SLSN models. Another unusual aspect was its ultraviolet spectrum. Most SLSN emit in the optical or near ultraviolet bands. Assassin 15LH, on the other hand, was extremely UV bright, with an emission profile that didn't quite match known SLSN. Its temperature was higher than expected, and it sustained that temperature for longer than the standard models could accommodate. Instead of cooling quickly as SLSN typically do, Assassin 15LH remained hot for an extended period, suggesting a prolonged or secondary energy injection mechanism. Then came the host galaxy conundrum. SLSN are usually found in small, irregular, star-forming dwarf galaxies. These galaxies are hotbeds of young, massive stars, the kind of stellar environments where superluminous supernovae are believed to originate. Assassin 15LH's host was the polar opposite, a massive, old, elliptical galaxy with little to no star formation. This was a profound contradiction. If Assassin 15LH really was an SLSNI, then its location made little sense. Where was the progenitor star supposed to come from? Massive stars don't live long, and they don't form in dead galaxies. As astronomers continued to dig deeper into the data, other issues arose. The spectra of Assassin 15LH lacked many of the broad, defining features of superluminous supernovae. There were no clear indicators of the typical heavy elements expected from a stellar explosion of this magnitude. In fact, some of the spectral lines were so weak and ambiguous that they defied confident interpretation altogether. This led to growing skepticism within the astronomical community. Was Assassin 15LH really a superluminous supernova, or were astronomers trying to fit a square peg into a round hole? Could it be something else, something even stranger? Some tried to make the SLSNI model work by proposing an extreme version of the Magnetar hypothesis. Perhaps, they suggested, Assassin 15LH was powered by an unusually fast-spinning neutron star with an incredibly strong magnetic field. But even with unrealistic spin rates and magnetic strengths, the model still fell short of accounting for the energy output and light curve behavior of Assassin 15LH. The numbers just didn't add up. Others proposed that the explosion involved interaction with circumstellar material, CSM, clouds of gas and dust surrounding the progenitor star that could, in theory, re-energize the light curve through shock interaction. But this kind of interaction usually leaves behind telltale spectral fingerprints, and Assassin 15LH didn't show them. It was as though the universe was deliberately hiding its clues. As the months passed and the observations accumulated, the theory that Assassin 15LH was a typical, or even atypical, superluminous supernova began to crumble. The inconsistencies were too many. Its light curve, spectrum, location, and energy output all suggested that if it was a supernova, it was one of a kind, an extreme outlier in every measurable sense. And perhaps, it wasn't even that. Still, the classification remained for a time, not because it fit well, but because no better alternative had yet emerged. Astronomers needed a working model, even a flawed one, to begin testing against new data. In that sense, the label, superluminous supernova, became more of a placeholder, a sign that Assassin 15LH was something powerful and luminous and transient, even if it didn't play by the established rules. Eventually, more radical ideas would gain traction, including the possibility that this was not a supernova at all, but rather the destruction of a star by a black hole, or something entirely unknown. But before those theories could take root, the astronomical community had to confront the simple, uncomfortable truth. If Assassin 15LH is a superluminous supernova, it's unlike any other we've ever seen, and it breaks nearly every rule in the book. In that way, Assassin 15LH both fits the mold and defies it. It wears the mask of a superluminous supernova, but the closer we look, the more the disguise slips. It is as if the universe allowed us to glimpse something masquerading as a familiar phenomenon, only to pull the rug out from under our assumptions. And just as astronomers were trying to reconcile its extraordinary features with known supernova models, the narrative would soon pivot in an entirely new direction, toward a phenomenon involving black holes, gravitational forces, and the shredding of stars on a scale no human had ever witnessed. When Assassin 15LH was first detected, its sheer luminosity demanded a prompt classification, if only to provide a framework for scientists to begin analyzing it. Based on the early data, particularly its spectrum and lack of hydrogen, astronomers swiftly categorized it as a Type 1 superluminous supernova, SLSNI. This was not a reckless assumption. In fact, at the time, it was the most logical choice. But as we now know, this classification, while initially helpful, would eventually be challenged on nearly every front. To understand why it was initially labeled as SLSNI, we must first explore what defines this category in astrophysical terms. A Type 1 superluminous supernova is an extremely rare kind of stellar explosion. Unlike typical Type 2 supernovae, which exhibit clear hydrogen lines in their spectra, Type 1 SLSNA are hydrogen-poor. Their defining feature is their extraordinary luminosity, up to 100 times brighter than standard core collapse supernovae, and their light curves, which show a slower rise and a prolonged decline in brightness compared to ordinary supernovae. The prevailing theory for most Type 1 SLSNA is that they're powered by a central engine, typically a magnetar, a highly magnetized neutron star formed during the collapse of a massive star. The magnetar injects energy into the expanding supernova ejecta, acting like a cosmic dynamo that sustains brightness for longer periods. In this context, a lack of hydrogen in the spectrum is expected because the progenitor star would have shed its hydrogen envelope before the collapse. Furthermore, these explosions tend to occur in low metallicity, star-forming dwarf galaxies, where the formation of massive stars is still actively occurring. When Assassin 15LH's light curve and spectrum were first analyzed in mid-2015, it exhibited some hallmark features of this class. The early spectrum showed a blue continuum, a characteristic signature of a hot and young supernova. It lacked hydrogen and helium features, reinforcing the hydrogen-poor Type 1 classification. The light curve indicated a smooth rise over the course of several weeks, and the peak luminosity was unprecedented, roughly 570 billion times brighter than the Sun, or over 20 times more luminous than the previous record holder in the SLSN category. So, from a procedural standpoint, the classification made sense. The team responsible for its discovery, ASSN, the All-Sky Automated Survey for Supernovae, working with collaborating astronomers around the world, had to fit the event into some known framework. At the time, no existing model explained the brightness of Assassin 15LH, but the SLSNI category offered at least a provisional identity. Papers were quickly published identifying it as the brightest supernova ever recorded, specifically of the SLSNI subtype. Almost immediately, however, murmurs of doubt began to arise. One of the first and most curious oddities was the host galaxy. As mentioned earlier, most SLSNI events occur in galaxies bustling with star formation, typically small, irregular galaxies rich in gas and young stars. These environments are fertile ground for massive stars to be born and to eventually end their lives in explosive events like supernovae. But Assassin 15LH's host galaxy was the exact opposite, a large, old, quiescent elliptical galaxy with very little star-forming activity. It was a puzzling match. Adding to the suspicion was the lack of strong spectral features. Even though the early spectrum was consistent with a hot, young explosion, it was surprisingly featureless. Over time, typical SLSNA develop absorption lines corresponding to elements such as oxygen, magnesium, and calcium as the ejected material cools. In Assassin 15LH's case, these lines were weak, poorly defined, or completely absent. Moreover, as astronomers continued monitoring the object, its light curve evolved in unexpected ways. After its initial rise and decline, patterns consistent with a typical supernova, it suddenly began brightening again, weeks after the peak. This rebrightening phase was especially perplexing, as it suggested an additional energy source was at play, one that didn't fit neatly into the Magnetar-powered model used to explain most SLSNI. The spectral evolution was also strange. Usually, after a supernova peaks in brightness, the expanding shell of gas cools and reveals more chemical signatures in the spectrum. However, Assassin 15LH's spectrum remained unusually blue and featureless even as it entered this late phase, behaving less like a typical SLSNI and more like an entirely new kind of event. In essence, scientists found themselves grappling with a paradox. They had an event that resembled an SLSNI in some superficial ways, high luminosity, blue continuum, hydrogen pure, but violated so many other criteria that it no longer seemed to belong to the class at all. It was like finding a panda bear that roars like a lion, climbs like a goat, and swims like a fish. You could call it a panda for convenience, but deep down, you know something didn't add up. In the background, other astronomers began proposing alternative interpretations. One of the most intriguing possibilities to emerge was that Assassin 15LH might not be a supernova at all, but rather a tidal disruption event, a cataclysmic flare caused when a star gets torn apart by the gravitational forces of a supermassive black hole. This theory began gaining momentum as scientists dug deeper into the details that didn't align with the SLSNI explanation. Despite the mounting inconsistencies, the SLSNI classification lingered for some time, largely because the astrophysical community didn't yet have a robust alternative model. Classification in astronomy is not always a precise science. It's often about best-fit models based on available data. But as the evidence piled up, it became increasingly clear that Assassin 15LH was something else, perhaps something the universe had never shown us before. The term, Type 1 superluminous supernova, served as a starting point, a placeholder, a framework around which data could be organized and hypotheses tested. But in the case of Assassin 15LH, that label soon began to feel more like a straitjacket than a guidepost. And so, the scientific conversation pivoted. If this wasn't a supernova, at least not in the conventional sense, then what was it? That's when astronomers turned their attention toward a radically different explanation, one rooted not in the death throes of a massive star, but in the immense gravitational forces lurking at the centers of galaxies. The idea of a tidal disruption event began to take shape, not just as a competing theory, but as a possible key to one of the brightest and most mysterious explosions the cosmos has ever witnessed. The initial classification of Assassin 15LH as a Type 1 superluminous supernova gave astronomers a temporary foothold, an interpretive lens through which they could begin understanding its extraordinary nature. But that lens would soon begin to crack. Almost as soon as the astronomical community accepted the idea that this was the most luminous supernova ever detected, unsettling data began to surface. Data that didn't just question the supernova model but outright defied it. The first major red flag was its host galaxy. Most superluminous supernovae, especially of the hydrogen-pure Type 1 variety, tend to erupt in dwarf galaxies rich in star formation. These galaxies, although faint and irregular in shape, are bustling nurseries for massive young stars, which are prime candidates to end their lives in such colossal explosions. But Assassin 15LH didn't occur in such a place. Instead, it was located in a massive, old, and quiescent galaxy, one with very little, if any, ongoing star formation. This immediately raised eyebrows. If massive stars weren't being formed there, what kind of star could have exploded? Why would the most luminous supernova ever detected occur in a galaxy environment that seemingly lacks the necessary ingredients? The elliptical host galaxy simply didn't fit the profile. Then came the strange behavior of the light curve, the graph showing its brightness over time. Initially, it seemed consistent with a superluminous supernova, a gradual rise in brightness followed by a slower decline. But after the peak, something unusual happened. Instead of fading steadily, Assassin 15 LH plateaued, and then it brightened again. This secondary rise, occurring around 90 days after the peak, was unlike anything astronomers had ever seen in a supernova. Typical supernovae decline in brightness smoothly as the expanding gas cools and the energy fades. A late-time bump in brightness implied a second source of energy. What was powering this resurgence? The spectrum also offered little comfort. In supernova observations, astronomers usually monitor the spectrum of the event over time, watching for characteristic lines that signify the presence of various elements like oxygen, magnesium, or iron. In Assassin 15 LH's case, its spectrum remained remarkably featureless and persistently blue, even months after its peak brightness. Normally, as the ejecta cools and becomes more transparent, it reveals the chemical fingerprints of the exploded star. But Assassin 15 LH stubbornly refused to conform, as though hiding its identity behind a veil of pure radiation. Another oddity came from temperature estimates. Most supernovae cool rapidly after the initial explosion. But Assassin 15 LH remained exceptionally hot for an unusually long time, suggesting that whatever was energizing it was not a brief radioactive decay process, as is the case in normal supernovae, but something more sustained, something still pumping energy into the system weeks or even months after the event began. This lingering heat and light couldn't be explained by conventional models. In a standard superluminous supernova, the energy might come from the radioactive decay of nickel-56, or from a magnetar, a rapidly spinning neutron star formed during the core collapse. But Assassin 15 LH was so energetic that these scenarios began to look increasingly implausible. To match its brightness, a magnetar would have to be spinning at a rate near the theoretical maximum, with a magnetic field stronger than anything previously observed. And even then, it wasn't enough. When the numbers were plugged in, the magnetar model came up short. It couldn't explain the peak luminosity and the late-time rebrightening. Something else had to be at work. Then there was the question of the expansion velocity, how fast the material was moving away from the explosion. In many supernovae, especially those with high luminosity, the outer layers are expelled at astonishing speeds, leaving telltale signs in the spectrum through Doppler-shifted absorption lines. But in Assassin 15 LH, these features were either weak or absent. The velocity data was inconsistent, muddled, and difficult to interpret. Some measurements implied relatively slow-moving material, which didn't match the explosive scale implied by its brightness. This unusual combination of features, a luminous yet featureless spectrum, anomalous light curve behavior, host-galaxy mismatch, and unfathomable energy requirements, all began to unravel the initial narrative. The very thing that had defined Assassin 15 LH in the public and scientific imagination, its classification as a supernova, was now being questioned at the deepest level. The more astronomers looked at it, the more it seemed that Assassin 15 LH was something altogether different, something not yet represented in astrophysical textbooks or known cosmic events. The doubts reached a boiling point when several teams began proposing that the event wasn't a supernova at all, but rather a tidal disruption event, or TD. A TD occurs when a star strays too close to a supermassive black hole, only to be torn apart by its immense gravitational forces. This scenario seemed to resolve some of the contradictions. For instance, TDs are more likely to occur in massive, quiescent galaxies, just like the one that hosted Assassin 15 LH. Also, TDs can produce extreme luminosities and may result in light curves with multiple peaks, especially if the accretion of stellar material onto the black hole is uneven. But even here, the mystery deepened. If it was a TD, where were the usual X-ray and UV signatures that such events produce? The follow-up observations didn't detect the strong X-ray outbursts typically associated with a black hole tearing a star apart. Moreover, TDEs generally show evidence of the stellar material being shredded and heated into an accretion disk, but Assassin 15LH lacked these clear signals. This duality, too luminous for a known supernova, too strange for a textbook TDE, led scientists to entertain even more exotic ideas. Could it be a new kind of stellar collapse? A hybrid event where a massive star implodes near a black hole, producing a combination of phenomena? Could it even be the first observed event of an entirely new astrophysical category? As each new paper was published and each new model tested, the doubts about Assassin 15LH's original classification grew louder. While the label, superluminous supernova, might have given the event a temporary home, it was becoming clear that this cosmic explosion was a homeless enigma, a brilliant orphan whose parentage was still entirely unclear. The astronomical community, usually grounded in well-defined frameworks and consensus, found itself dealing with something unfamiliar, an object that didn't just stretch the limits of current theory, it obliterated them. And in doing so, it posed a bigger question: what else are we missing out there? If the universe could produce something like Assassin 15LH without warning or precedent, what other astrophysical surprises lie hidden in the shadows of our data? This shift from certainty to speculation didn't represent failure. It marked the beginning of a new frontier. Doubt, in science, is the engine of progress. And Assassin 15LH, with its impossible brightness and rebellious behavior, had become the ultimate spark for reimagining what the cosmos is capable of. The idea that Assassin 15LH might not be a supernova at all, but instead the cataclysmic result of a tidal disruption event, TDE, quickly gained traction once the standard supernova models failed to fully explain its extraordinary behavior. A tidal disruption event occurs when a star ventures too close to a supermassive black hole lurking at the center of a galaxy. The gravitational gradient across the star, immensely stronger on the side closer to the black hole, becomes so extreme that the star is pulled apart in a spectacular and violent fashion, a process often described as the star being spaghettified. Once torn apart, roughly half of the star's mass is ejected into space, while the other half becomes bound to the black hole, spiraling inward to form a rapidly rotating, superheated accretion disk. This swirling disk of stellar debris emits staggering amounts of energy, primarily in the ultraviolet and X-ray parts of the electromagnetic spectrum, as the matter is compressed and heated to millions of degrees before vanishing into the event horizon. It's this radiant energy that can mimic the brightness of a supernova, and in some cases, even exceed it. In the case of Assassin 15LH, the brightness, duration, and behavior of the event led many astronomers to entertain the TDE hypothesis. Unlike standard supernovae that are powered by the radioactive decay of nickel-56 or the birth of a magnetar, TDEs draw their energy from gravitational forces, tapping into the nearly bottomless well of energy that resides in the immense mass of a black hole. Such an event can, in theory, produce a luminosity comparable to or even surpassing the most powerful supernova explosions. A key aspect that lent credibility to the TDE idea was location. Assassin 15LH's apparent proximity to the center of its host galaxy, a massive, quiescent elliptical, was suspiciously similar to where most TDEs are thought to originate. The galactic center is the natural domain of supermassive black holes, and in older, more passive galaxies like the one that hosted Assassin 15LH, the low levels of star formation make core collapse supernovae rare. If there was no ongoing formation of massive stars, the idea that a massive star suddenly exploded in a supernova seemed increasingly unlikely. But the presence of a dormant black hole, waiting quietly until an unlucky star wandered too close, that was far more plausible. Another piece of circumstantial evidence came from the light curve behavior, the unexpected second brightening after the initial decline. In TDEs, this kind of complex luminosity profile can occur due to variations in how the disrupted material is accreted onto the black hole. If the flow of stellar debris isn't smooth, if it clumps, precesses, or is interrupted by shocks, then the brightness could rise again as new material reaches the accretion disk and ignites in a renewed burst of radiation. This isn't typically seen in supernovae, but it aligns with certain models of TDEs. Furthermore, the blue and hot spectral signature that persisted over months also matched characteristics seen in other known TDEs. These events often show minimal spectral features and maintain high temperatures for extended periods, as opposed to cooling rapidly like supernovae. In Assassin 15LH, the lack of metal-rich absorption and emission lines, as well as the absence of significant velocity signatures in the spectra, made more sense in the context of a black hole feeding on a shredded star than in the usual framework of a star violently expelling its own layers in a supernova. Still, the tidal disruption theory wasn't without its own complications. For one, Assassin 15LH was far more luminous than any TD previously observed, by a factor of 10 or more. If this was indeed a TD, it wasn't just any TD, it was a monster, an outlier so extreme that it forced scientists to consider whether we were seeing a new subclass of tidal disruptions, perhaps occurring in the presence of unusually massive black holes or under highly specific conditions. One intriguing possibility was that the black hole involved might be an intermediate mass black hole, a hypothetical class of black hole more massive than stellar mass ones but smaller than the supermassive variety, ranging from hundreds to thousands of solar masses. These objects are rare and elusive, but if such a black hole existed in a compact star cluster or a satellite system within the host galaxy's center, it could have interacted with a star in just the right way to trigger a highly energetic TD. Alternatively, the central black hole could have been spinning at near-relativistic speeds. A rapidly rotating Kerr black hole can significantly increase the energy release during a TD, especially if the spin and the orbital trajectory of the infalling star are favorably aligned. This kind of energetic amplification might be necessary to explain the luminosity of Assassin 15LH. Additionally, theorists considered the impact of general relativity on such an event. As a star approaches the event horizon of a black hole, extreme relativistic effects begin to dominate. The intense warping of spacetime could alter the accretion dynamics, magnifying the observed brightness depending on the angle of observation and the energy dissipated in the inner accretion regions. If Assassin 15LH was a TD happening at just the right geometry, perhaps with jets of material pointing almost directly toward Earth, it might have appeared far brighter than it actually was, a kind of relativistic beaming effect. Despite all these appealing facets of the TD hypothesis, there were also nagging issues. X-ray observations from the Swift Observatory and other instruments failed to detect the strong X-ray signals that would typically accompany a TD. While not all TDs produce X-rays at detectable levels, especially if the X-ray emissions are absorbed by intervening material or if the disk never gets hot enough, the absence of these emissions cast doubt on the scenario. Moreover, the event's extreme luminosity raised the possibility that the central black hole might be too massive. Tidal disruption events can only occur if the black hole's tidal radius, the point where the star gets shredded, lies outside its event horizon. But if the black hole is above a certain mass threshold, roughly 10 to the power of 8 solar masses, then most stars would simply vanish without a trace, swallowed whole before they could emit any radiation. Some estimates of the host galaxy's central black hole mass suggested it might lie uncomfortably close to or even above this threshold, making a standard TD theoretically impossible. Unless, of course, something more exotic was happening. This paradox led to deeper theoretical discussions about partial TDEs, where a star merely grazes the black hole and is only partially disrupted, or events where a compact object like a white dwarf is tidally destroyed by an intermediate mass black hole in a dense stellar cluster, rather than the galactic center. Could Assassin 15LH represent such a rare occurrence? As the debate raged, more observational campaigns were launched to search for similar events, to probe the late-time behavior of Assassin 15LH, and to model the energy dynamics in greater detail. The TD hypothesis remained tantalizing, but not definitive. It explained much, but not everything. And like the supernova hypothesis before it, it eventually hit a wall of inconsistencies and unanswered questions. So astronomers were left once again in the gray zone of cosmic uncertainty. Perhaps Assassin 15LH wasn't a traditional supernova, nor a classic TD. Maybe it was something in between, or entirely outside the dichotomy we had grown used to. It was as if nature, in its boundless complexity, had thrown a curveball at our models, daring us to imagine phenomena we hadn't yet theorized. And in doing so, Assassin 15LH reminded the scientific community of a humbling truth. Sometimes, the universe doesn't just challenge our understanding, it obliterates the categories we've built to contain it. To truly grasp the tidal disruption event hypothesis proposed for Assassin 15LH, we need to step back and understand what tidal disruption events, or TDEs, actually are, how they happen, what they look like, and why they're so rare and fascinating in modern astrophysics. Imagine a galaxy's core, quiet and seemingly still, harboring a sleeping monster, a supermassive black hole. These colossal objects, with masses millions or even billions of times that of our Sun, typically lurk in the hearts of galaxies, invisible yet influential, pulling on the stars and gas that surround them with an iron grip of gravity. For the most part, these black holes remain dormant. Unless they're actively feeding, such as in a quasar or an active galactic nucleus, they emit no visible light. They simply wait, hidden in the dark. But every now and then, a star gets too close. It might be a wandering star from the outskirts of the galactic core, or perhaps a member of a dense nuclear star cluster whose orbit slowly decayed over millennia. Whatever the origin, as soon as the star crosses the black hole's tidal radius, the point where the black hole's gravitational pull is stronger across the diameter of the star than the star's own self-gravity, something extraordinary happens. The star is stretched and compressed at the same time in a process called spaghettification. The term might sound whimsical, but the physics behind it is terrifying. The gravitational gradient becomes so steep that the star is pulled into a long stream of stellar matter, torn apart strand by strand, atom by atom. This is the beginning of a tidal disruption event. After the star is torn asunder, its fate is split, literally. About half of the stellar debris gains enough kinetic energy to be flung out into space, perhaps even escaping the galaxy entirely. The other half, however, remains bound to the black hole. This matter spirals inward, forming an accretion disk, a rapidly rotating ring of intensely hot gas swirling ever closer to the event horizon. Friction within this disk causes the material to heat up to millions of degrees, emitting immense amounts of radiation in ultraviolet, optical, and even X-ray wavelengths. The result is a brilliant flare of light that can shine as brightly as a billion suns. To an observer on Earth, this manifests as a sudden outburst from the heart of a galaxy, a luminous beacon in the sky that wasn't there days or weeks before. Tidal disruption events were purely theoretical for much of the 20th century, predicted from Einstein's theory of general relativity and from calculations involving gravity's effects on extended objects. But in the last few decades, improvements in sky surveys, telescopes, and data processing techniques have finally allowed us to catch these rare events in real time. One of the earliest confirmed TDEs was detected in the 1990s, but since then, dozens more have been observed, each offering new insights into how stars interact with black holes. What's particularly intriguing is that TDEs can serve as natural laboratories for black hole physics. When black holes feed, they reveal themselves. Their masses can be inferred from the light curves of the flare. The composition of the star can be studied from the emission lines in the spectrum. Even the spin of the black hole can sometimes be estimated based on the energetic output and timing of the event. It's a rare chance to study these otherwise silent giants. Most TDEs follow a relatively standard pattern. There's a sharp rise in brightness as the stellar debris begins to fall into the black hole, followed by a gradual decline over months or years. The light emitted is often blue and extremely hot, around 30,000 to 100,000 Kelvin, because of the extreme temperatures of the inner disk. Spectroscopically, the events might show broad hydrogen and helium lines, or even high ionization lines, depending on the composition of the disrupted star and the dynamics of the accretion. However, not all TDEs are created equal. Some are jetted TDEs, where the black hole emits relativistic jets, streams of plasma traveling near the speed of light, often in the direction of Earth. These events tend to be accompanied by strong X-ray or radio emission and can be even brighter than traditional TDEs. Others are non-jetted TDEs, which emit only in optical or UV light and fade more slowly. The diversity among observed TDEs suggests that their appearance depends on many factors: black hole mass, stellar type, impact angle, viewing geometry, and whether or not the disrupted material forms a stable disk. Now, when scientists looked at Assassin 15LH, they saw certain features that at least partially matched a TDE profile. Its location near the center of its host galaxy, for example, was suspiciously consistent with where supermassive black holes reside. Its light curve, though unusual, had elements that resembled the fallback accretion rate expected after a TDE. And its persistently hot temperature over an extended period also made sense within this framework. But here's the catch: Assassin 15LH was far brighter than any TDE ever recorded, nearly an order of magnitude more luminous than known tidal disruptions. That forced astronomers to ask, is it possible that we've only observed a limited subset of TDEs so far, and Assassin 15LH simply belongs to a more energetic class we haven't encountered before? Or did it involve a different kind of black hole, a spinning one, perhaps? Or a more massive star? Some theorists propose that Assassin 15LH could have been a TDE involving a white dwarf, a dense, compact remnant of a dead star, being disrupted not by a supermassive black hole, but by an intermediate mass black hole, IMBH. Such black holes are believed to exist in globular clusters or dwarf galaxies, and although none have been definitively confirmed, they are thought to range between 100 and 100,000 solar masses. In this kind of event, a white dwarf might emit radiation much more efficiently as it disintegrates, explaining the extreme brightness of Assassin 15LH. Another model suggested a rapidly spinning Kerr black hole, which, due to its angular momentum, could stretch the tidal radius further out and boost the energy output through frame dragging and relativistic effects. If Assassin 15LH happened under these highly specific, exotic conditions, it might qualify as an ultra-rare TDE variant. But the problem wasn't just brightness, it was also duration. Assassin 15LH stayed bright for an exceptionally long time, nearly doubling its light curve in a strange secondary rise, and maintaining high temperature and luminosity far beyond what typical TDE models would predict. This complex evolution in brightness hinted at more chaotic and unpredictable accretion behavior, or even a series of interactions between the debris streams themselves. Moreover, many typical TDEs emit copious amounts of X-rays, as hot gas near the black hole heats up to extreme temperatures. But Assassin 15LH, despite being observed by instruments like the Swift Observatory, showed no strong X-ray signal, leaving a major hole in the TDE explanation. This inconsistency forced astronomers to ask whether some new kind of TDE physics was at play, or if Assassin 15LH wasn't a TDE at all. Ultimately, tidal disruption events remain one of the most compelling alternative explanations for what happened in 2015 when Assassin 15LH lit up the sky like nothing before. They offer a framework that explains the location, longevity, and potentially the energy, if certain parameters are stretched or reimagined. But they don't answer all the questions. In fact, like the supernova hypothesis, the TDE scenario eventually begins to wobble under the sheer weight of Assassin 15LH's extremity. That's what makes this cosmic enigma so enduring. Every hypothesis, however promising, seems to fray at the edges the more we look. And yet, through the lens of tidal disruption events, Assassin 15LH reminds us how violent, unpredictable, and awe-inspiring the relationship between stars and black holes can be. In those moments when the universe tears itself apart, it leaves behind a flash of light that can outshine the entire galaxy, and a mystery that can puzzle us for decades. There are countless spectacular events unfolding in the cosmos: cataclysmic collisions, stellar deaths, galaxy mergers, black holes feeding, neutron stars colliding, but even amid this eternal drama, Assassin 15LH stands alone. To understand what truly sets it apart, we must examine its behavior in three distinct but interwoven aspects: the energy it released, the duration of its light curve, and the strangeness of its location. Each one on its own would be enough to catch astronomers' attention. Together, they defy almost every astrophysical model we've built so far. Let's begin with the raw energy. When Assassin 15LH exploded, or erupted, or tore apart, depending on what it actually was, it released a staggering amount of energy. Over its peak luminosity period, it radiated light at a rate 570 billion times brighter than our Sun. Not just once. Not briefly. But continuously, for weeks and months. The integrated total energy output, or the full tally of its radiant energy over time, amounted to something on the order of 10 superscript 2 ergs. That's 10 followed by 52 zeros, roughly equivalent to the combined energy of hundreds of normal supernovae. Even the most powerful Type I or Type II supernovae, long considered the titans of stellar death, don't come close to this energy release. Nor do Magnetars under standard assumptions. Most known superluminous supernovae top out around a few times 10 ergs per second in peak luminosity. Assassin 15LH reached over 2 times 10 ergs per second, essentially requiring a mechanism that not only surpasses but redefines what we thought was possible from a dying star. Now, massive energy output is one thing, but what made it even more extraordinary was how long Assassin 15LH remained active. A typical supernova brightens rapidly, peaks over a few days to a week, and then begins a gradual decline as the explosion fades and the radioactive elements, like nickel-56, decay. Even the most extreme supernovae tend to drop off after a few months. But Assassin 15LH didn't just linger, it evolved in a way that stunned astronomers and telescopes alike. After its initial peak in July 2015, observers expected the brightness to fade, and it did, at first. But then something very unusual happened. Around 90 days later, the light curve stopped fading and began rising again. This secondary brightening phase persisted for an additional 120 days. It was as if the engine powering the explosion had roared back to life, something no existing model could easily explain. Not only was this rebrightening rare, it occurred without the typical signs of interaction that are usually present when supernovae collide with dense circumstellar material. There was no prominent hydrogen emission in the spectra, no shock signatures, no X-ray spikes that might point to an external energy input. Instead, Assassin 15LH's light curve suggested that whatever mechanism had powered it initially had either restarted or continued burning with bizarre consistency. The temperatures during this period remained incredibly high, over 20,000 Kelvin, and its ultraviolet output remained strong, a clear indicator that the explosion or event hadn't cooled off the way supernovae typically do. This extreme longevity alone pushed theorists into unfamiliar territory, demanding answers from models that weren't designed to handle such extreme durations. And then there's the final piece of this celestial puzzle, its location. Supernovae, as a rule of thumb, tend to occur in star-forming regions of spiral galaxies or irregular galaxies where massive stars live and die. That's because the progenitors of supernovae, massive stars with at least 8 solar masses, are relatively short-lived. They burn bright and die young, typically in galaxies with active stellar nurseries and dynamic, dusty arms. But Assassin 15LH occurred in a massive, old, red, and quiescent galaxy, a type of galaxy known as a luminous red galaxy, LRG, which has long since finished its star-forming activity. This kind of galaxy is dominated by aged, low-mass stars. There are no new, massive, short-lived stars being born in this environment. That makes it one of the least likely places for a traditional core collapse supernova, and even for most superluminous supernovae, which are almost exclusively found in small, irregular, and actively star-forming galaxies. This paradoxical location puzzled astronomers from the start. Was there some rare pocket of star formation in this red galaxy that no one had noticed? Spectroscopic surveys showed otherwise. The galaxy showed little or no signs of recent star formation or residual gas. If the event wasn't a core collapse supernova, and the galaxy didn't house the types of stars that explode in that way, then what was Assassin 15LH? This is why alternative explanations gained so much traction. If the event had occurred at the center of the galaxy, and it did appear to lie very near the galactic nucleus, then perhaps it was not a star dying, but a star being torn apart, hinting at a tidal disruption event. But as discussed previously, even that theory struggles to account for the light curve, energy, and spectral behavior without invoking additional exotic ingredients like rapidly spinning black holes or unusually massive stellar remnants. Even stranger, some speculative models propose that this might have been a hybrid event, the collapse of a massive star in the vicinity of a black hole, where the resulting explosion was modified or amplified by the black hole's gravity, magnetic field, or radiation environment. These hybrid models are still theoretical and lack observational precedent, but Assassin 15LH is so outlandish that it has essentially forced astrophysicists to begin crafting such frameworks. Adding to the uniqueness is the object's host galaxy redshift, which placed it about 3.8 billion light-years away, not the most distant supernova ever detected, but far enough to indicate that this wasn't some rare local anomaly. It's part of the broader cosmic landscape, suggesting that such phenomena might occur elsewhere too. Perhaps we've simply lacked the sensitivity to detect them until now. So, taken together, Assassin 15LH wasn't just bright. It wasn't just long-lasting. It wasn't just unusually placed. It was all three, all at once, breaking rules across the board. Its light output exceeded theoretical limits. Its behavior over time defied expectations. And its location shattered assumptions about where such events should occur. Each of these anomalies might be reconcilable in isolation, with the right theoretical bandages. But together they form a riddle that resists all easy answers. In many ways, Assassin 15LH has acted like a stress test for astrophysical theory. It sits at the limits of what we believe the universe can do, and perhaps just beyond. It's the cosmic equivalent of discovering a creature that bleeds gold, lives 300 years, and was found swimming in a desert. You can explain away one of those things. Two might raise eyebrows. But all three? You begin to realize something unprecedented has happened. This is why Assassin 15LH continues to spark debates, models, and publications years after its discovery. It refuses to fit inside the neat boxes of our current understanding. And maybe, just maybe, it's pointing toward a new category of astrophysical events that we've only just begun to glimpse. The mystery of Assassin 15LH only deepens when we examine the environment in which it occurred, the host galaxy. In the study of cosmic explosions, the context of the event often reveals key clues about its origins. A supernova's host galaxy is like a crime scene for astrophysicists. It holds fingerprints, environmental hints, and even motive. But when Assassin 15LH exploded, astronomers quickly realized that the galactic setting didn't just offer a mystery. It complicated everything. To understand why, consider the types of galaxies we normally associate with superluminous supernovae, SLSna. Most of these events are discovered in small, irregular, and actively star-forming galaxies. These galaxies are teeming with massive, short-lived stars, ideal candidates to go out in a blaze of cosmic glory. In fact, before Assassin 15LH, nearly all known SLSna had been linked to low-mass galaxies with intense star formation activity. That was a key point in the emerging theory of how SLSna worked. You needed big stars, freshly born, dying young. But Assassin 15LH broke that mold entirely. It erupted not in a young, star-forming galaxy, but in a massive, old, red, and quiescent elliptical galaxy. More specifically, it was detected in a luminous red galaxy, LRG, a type of galaxy that had long since burned through its star-forming fuel and settled into cosmic retirement. These galaxies are typically composed of aging, low-mass stars, with little or no evidence of the active star formation required to produce the kind of massive progenitor stars that give rise to supernovae, let alone superluminous ones. This mismatch sent a shockwave through the astrophysics community. How could such an energetic event, potentially the most powerful supernova ever observed, have come from a galaxy so completely unsuited to producing it? One of the first detailed follow-ups came from the Hubble Space Telescope, which zoomed in to study the host galaxy of Assassin 15LH in exquisite detail. The Hubble data confirmed the galaxy's status as a massive elliptical system, with a red, evolved stellar population. Spectroscopic analysis revealed almost no signs of recent star formation, no blue regions, No emission lines that typically indicate hydrogen gas being ionized by young, hot stars. This galaxy wasn't just a poor candidate for forming massive stars, it was effectively sterile. Further analysis placed the stellar mass of the host galaxy at around 200 billion solar masses, making it significantly more massive than the Milky Way. But despite its size, it had none of the raw ingredients for new stellar life. That stark absence made the presence of Assassin 15 LH almost paradoxical. Adding another layer to this riddle was the location of the explosion within the galaxy. Assassin 15 LH was found almost perfectly centered within the nucleus of its host. This raised yet another flag. Supernovae don't usually happen at galactic centers. But you know what does? Tidal disruption events, where stars wander too close to the supermassive black holes that sit at the cores of most large galaxies. That's where the black hole scenario began to gain traction, but we'll return to that in more detail later. For now, let's pause and reflect on how significant this galaxy's profile really is. Imagine expecting to find a forest fire in a desert. A superluminous supernova like Assassin 15 LH was thought to require a high rate of massive star births, something that simply doesn't happen in red elliptical galaxies. The detection of such an extreme event in a place devoid of young stars not only challenged existing models, it undermined the very foundation of how we classify and locate stellar deaths. Even more curious was the fact that this wasn't just any elliptical galaxy. It was among the most massive and evolved of its kind. The host galaxy had a low specific star formation rate, a high mass-to-light ratio, and a spectral profile consistent with passive evolution over billions of years. This meant that if the event was truly a supernova, it had to come from a different kind of progenitor than we'd ever encountered before. There were other oddities too. Astronomers searching for signs of circumstellar material, shells of gas and dust that might have been shed by a dying star, found none. There was no evidence of hydrogen in the spectra, nor any of the usual signs of shock interaction that can occur when a supernova plows into the material its progenitor star ejected before dying. In other words, this explosion wasn't just happening in the wrong place. It was doing so without leaving behind the usual environmental clues. So what does this mean? First, it forces us to consider that not all superluminous explosions are created equal. There may be subclasses, or even entirely new categories of transient phenomena, that share some observational traits with SLSNA but arise from fundamentally different mechanisms. Second, it raises serious doubts about the standard Magnetar model for superluminous supernovae, because forming a rapidly spinning magnetar, a highly magnetic neutron star, requires the death of a young, massive star. But again, those stars simply shouldn't exist in a galaxy like this. This leaves theorists scrambling. Could an old white dwarf somehow trigger an ultraluminous thermonuclear explosion under rare conditions? Could two neutron stars have merged near a supermassive black hole, amplifying the resulting emission? Could the galactic center itself, perhaps via an interaction with the central black hole, have caused a star to ignite in an entirely novel way? All of these ideas have been explored, but none has yet provided a satisfying, self-consistent explanation that fits every piece of evidence. Each theory either fails to match the light curve, the spectrum, the energy, or the context. The more we learn about the host galaxy, the more it seems to actively contradict the traditional supernova narrative. This has prompted a philosophical shift in how we approach such events. No longer can we rely solely on what an explosion looks like in isolation. We now have to consider the where with as much weight as the what. The environment matters. The neighborhood tells a story. And in the case of Assassin 15 LH, that story is one of deep contradiction, a titanic explosion in a place where none should occur. Ultimately, the host galaxy mystery remains one of the most crucial pieces in the Assassin 15 LH puzzle. It challenges our assumptions, widens our models, and keeps the door open to new and radical possibilities. Perhaps, just perhaps, it even hints at a new kind of cosmic engine, one that is only now being glimpsed through anomalies like this. And if that's true, then Assassin 15 LH is not just an outlier, it's a signpost pointing toward uncharted regions of astrophysical reality. One of the most baffling elements of Assassin 15LH's story emerged not during its explosive arrival, but in the months that followed, as astronomers continued monitoring its fading glow and noticed something they weren't expecting. Like many other aspects of this object, its light curve, the graph showing how its brightness changed over time, refused to follow the script. Initially, everything appeared to be relatively standard for a superluminous supernova. The object brightened quickly, peaking in luminosity with astonishing brilliance, and then began the expected decline. But then came a twist. Roughly 2 months after it had peaked, Assassin 15LH began to do something that had virtually never been seen before in a confirmed supernova. It started getting brighter again. This unexpected second rise in brightness defied conventional models. In a normal supernova, and even in a superluminous one, the light curve typically features a sharp, energetic peak followed by a steady decline, shaped by the decay of radioactive nickel and cobalt, or in more energetic cases, by the energy injected from a central engine like a magnetar. The rule is simple: supernovae don't turn around and brighten again. But Assassin 15LH broke this rule. The light curve showed a complex and unusual rebrightening phase that began about 90 days after peak luminosity, and lasted for over 120 days. During this time, the total luminosity did not just plateau, it increased again significantly, particularly in the ultraviolet UV part of the spectrum. This second brightening added an enormous amount of energy to the event's already staggering output, making it even more of a cosmic outlier. Astrophysicists scrambled to understand this strange post-peak behavior. Was it evidence of some kind of additional energy input that had not been accounted for? Was Assassin 15LH interacting with some form of previously unseen circumstellar material, CSM, like a dense shell of gas shed by the progenitor star long before it exploded? That kind of interaction could conceivably produce a delayed shock that might show up as rebrightening, but this theory clashed with the fact that no clear spectroscopic signatures of CSM interaction, like hydrogen or helium lines, were present in the spectra. Another possibility involved accretion processes. If Assassin 15LH were not a supernova at all, but rather a tidal disruption event, TDE, the death throes of a star torn apart by a supermassive black hole, then the late-time rebrightening might be explained by delayed or resumed accretion of stellar debris onto the black hole. This would not be unprecedented. Some TDEs have shown complex, multi-phase light curves where matter falling into the black hole produces a resurgence in emitted energy. But even by TDE standards, Assassin 15LH's behavior was unusually energetic and prolonged. Complicating matters even more, the wavelength at which the light returned was heavily weighted toward the ultraviolet, rather than optical or infrared. This is not what you would expect from most shock interaction models, which tend to produce more thermalized, redder emission. The UV signature suggested that something extremely hot was reigniting or continuing deep within the system. It was almost as if the central engine had flickered, dimmed, and then roared back to life. Adding to the puzzle, some models attempted to resurrect the Magnetar hypothesis, arguing that the central neutron star might have experienced delayed energy injection. Perhaps, they speculated, a two-stage magnetic dipole wind occurred, where energy was released in bursts rather than in a smooth decline. But this model required very fine-tuned parameters and could not easily explain the duration and shape of the secondary peak. And then there was the duophase hypothesis, a novel idea that suggested Assassin 15LH could represent the combination of two physical mechanisms, an initial explosion, perhaps a magnetar-powered supernova or a TDE, followed by a second process, such as fallback accretion, delayed black hole feeding, or even the ionization of a previously ejected shell of gas. This approach aimed to reconcile the high peak luminosity with the strange rebrightening by treating the light curve as a kind of composite signal, two different engines running in sequence. While promising in concept, these models remain speculative, and none has been universally accepted. The mere shape of the light curve forced a major re-evaluation of how we interpret transient phenomena. For comparison, most SLSNA decline gradually but predictably. A bump, like the one in Assassin 15LH, is rare, and in such a high luminosity context, virtually unheard of. Even among known tidal disruption events, this kind of behavior is exceptional. In fact, the only vaguely similar light curve came from another peculiar transient called SN 2006 GY, which also showed extended emission, but that event was believed to be heavily influenced by dense CSM interaction, something lacking here. Moreover, Assassin 15LH's rebrightening phase helped astronomers estimate the total radiated energy of the event over its full evolution, something close to 2.2 times 10 superscript 2 ergs, an energy release that rivals the binding energy of a neutron star. This alone made it the most energetic transient event of its kind ever recorded, and the light curve was the map that revealed that colossal figure. In all, the strange behavior of Assassin 15LH's light curve represents one of its most baffling and consequential traits. It didn't just peak and fade. It pulsed. It breathed. It burned bright, dimmed, and then blazed again, sending a clear signal that whatever powered this object, it wasn't following known astrophysical rules. Each new model was like a key that turned the lock partway, but never quite opened the door. As data continued to pour in from telescopes around the world, each plotting the object's shifting brightness across weeks and months, one thing became clear: the light curve itself wasn't just a graph. It was a message, scrawled across billions of light years, saying, "This is not what you think it is." When astronomers encounter an extraordinary cosmic event like Assassin 15LH, one of their first instincts is to study its spectrum, the breakdown of its light into its component wavelengths. Much like a fingerprint, a light spectrum can reveal critical information about what something is made of, how fast it's moving, what temperatures it reaches, and even how it evolves over time. Spectral analysis lies at the heart of classifying supernovae, understanding their energy sources, and mapping the environments in which they occur. But in the case of Assassin 15LH, the spectrum gave as many riddles as it did answers, if not more. When Assassin 15LH was first observed spectroscopically shortly after its discovery in June 2015, astronomers noticed that its spectrum lacked the features typically expected in most known types of supernovae. There were no prominent hydrogen lines, which instantly ruled out a Type II supernova, the kind that results from the core collapse of massive stars surrounded by hydrogen-rich outer envelopes. There were also no clear helium lines, excluding Type IB events. In fact, the spectrum showed a curious absence of strong absorption or emission features entirely, which is extremely unusual. At first glance, the smooth, nearly featureless spectrum seemed to match loosely with the known class of Type I superluminous supernovae, SLSNI. These are a subclass of extremely bright explosions that are devoid of hydrogen in their spectra and are believed to arise from the deaths of massive stars that have been stripped of their outer layers. The spectra of SLSNI events are typically dominated by highly ionized oxygen, carbon, and magnesium lines in the ultraviolet and blue part of the spectrum. Assassin 15LH showed some weak indications of such elements, especially in the early stages. But even these hints were not conclusive or definitive. More intriguingly, as Assassin 15LH evolved over time, its spectrum became even less identifiable. It did not develop the typical P Cygni profiles seen in supernovae, which are characteristic absorption and emission signatures that provide velocity and expansion data. Nor did it show the late-time nebular features that would help reveal the composition of the ejecta as the material thinned out and allowed astronomers to see deeper into the explosion. Instead, what astronomers got was a muted, almost sterile spectral evolution, a phenomenon that only added to the mystery. One of the few recurring features was an absorption dip around 4,100 angstroms, a characteristic sometimes attributed to ionized magnesium, Mg2, but even this identification was debated. The rest of the light spectrum was dominated by a hot, featureless continuum, more similar to the spectra of active galactic nuclei, AGN, or quasars than to stellar explosions. This was a significant departure from expectations. If Assassin 15LH were a conventional SLSNI, the spectrum should have revealed more structure and stronger metal lines as the photosphere receded. Instead, it remained eerily consistent, even as the object faded over time. This odd behavior led some scientists to propose that perhaps the event wasn't a supernova at all, but rather a tidal disruption event, TDE, in which a star is torn apart by the gravitational forces of a supermassive black hole. TDEs are also known to produce blue, hot, and somewhat featureless spectra, especially in the early phases. They emit predominantly in the UV and soft X-rays, and their light curves can mimic the gradual decline observed in Assassin 15 LH. But again, Assassin 15 LH didn't line up perfectly with TDE expectations either. For example, most TDEs show clear signs of Balmer emission lines from hydrogen as stellar material spirals into the black hole. But these lines were conspicuously absent in the spectrum of Assassin 15 LH. Moreover, TDEs often show broader line features as the material whips around the black hole at extreme velocities. Here, the lines were either missing or too narrow to be consistent with high-speed stellar debris. The spectrum also defied modeling efforts. When teams attempted to use synthetic spectrum modeling, computational tools that simulate how light would look if emitted by specific physical scenarios, they found that no existing model could replicate the spectral shape of Assassin 15 LH across all wavelengths. Some models could fit the early time spectrum in isolation, and others could fit the late time brightness in select bands, but none could fit the entire observed data set simultaneously. What's more, the temperature inferred from the spectrum was extraordinarily high, above 20,000 Kelvin initially, cooling only slowly over several weeks. This indicated a very powerful and sustained energy source. In typical supernovae, especially Type I or even mini-core collapse events, the temperature drops relatively quickly as the ejecta expands and cools. But Assassin 15 LH maintained high thermal emission for an unusually long period, which again hinted at something deeper, or stranger, happening at the core of the event. This thermal persistence also had implications for its ionization environment. The fact that the spectrum remained so featureless meant that the light-emitting region was extremely hot and fully ionized, stripping electrons from atoms so thoroughly that they couldn't produce visible spectral lines. This is consistent with intense internal heating, perhaps from a magnetar, or from fallback accretion, yet neither model accounted for the lack of observed metal lines, which should still be present even at high energies, especially in the UV. Adding to the conundrum was the apparent lack of polarization in the light. When light from astronomical events is polarized, it suggests asymmetry in the source, perhaps jets, dust, or a disk structure. The near-zero polarization in Assassin 15 LH suggested a remarkably spherical source, or one where emissions were evenly distributed across our line of sight. This doesn't line up well with many TDEs, which are believed to involve flattened accretion disks or jet-like emissions. Ultimately, the spectral analysis of Assassin 15 LH provided more negative evidence than positive confirmation. It told scientists what the event was not, rather than what it was. It was not a normal supernova. It was not a hydrogen-rich explosion. It was not a classic TDE. And it didn't clearly match any model involving interaction with dense surrounding gas. What remained was a vague, persistent sense that this event was simply outside the bounds of current spectral classification schemes. Even today, years after the event, Assassin 15 LH's spectrum remains an enigma in astrophysical archives. Researchers continue to pore over the data, trying new modeling techniques, machine learning classification tools, and hybrid hypotheses to make sense of what they see. The spectrum might still hold the key to understanding the event, if only scientists can ask the right question, or build the right model to decode it. One thing is certain, for all the light Assassin 15 LH cast across the cosmos, it has kept its deepest truths in the shadows, hidden within a spectrum that speaks more in riddles than revelations. Despite years of rigorous study, intense debate, and data collected from some of the most advanced instruments humanity has ever built, Assassin 15 LH remains, to this day, one of the most puzzling cosmic events ever recorded. Why is the cause still unclear? Why, even after countless hours of computational modeling, spectral analysis, and multi-wavelength observation, do scientists still not agree on what Assassin 15 LH truly was? The answer, like the universe itself, is not simple. It is rooted in a complex web of contradictions, model failures, data limitations, and the persistent possibility that Assassin 15LH is not just a strange member of a known category, but something altogether new. To begin, Assassin 15LH defies classification because it breaks the physical limits of known astrophysical models. When a new supernova is discovered, scientists generally follow a well-worn path. They examine the light curve, the spectrum, the brightness, the temperature, and the context of the host galaxy. Then they compare these observations to thousands of known events catalogued over decades. In most cases, an event fits neatly, or at least roughly, into a classification. Type I, Type 2. Core collapse. Superluminous. But Assassin 15LH shatters the mold at every turn. First, there is the unprecedented luminosity. At its peak, Assassin 15LH radiated energy at a rate about 570 billion times that of our Sun, or around 20 times brighter than the entire Milky Way galaxy. This single point in space, for a brief moment, outshone hundreds of billions of stars. Such intensity isn't just rare, it's theoretically problematic. The leading explanations for such brightness, like the Magnetar model or radioactive decay of nickel, quickly hit energy ceilings. There's simply no known mechanism in standard stellar physics that can account for that level of sustained output without running into severe contradictions with what we know about matter, pressure, gravity, and energy conservation. Then, there's the light curve behavior, the pattern of how the brightness rose and fell over time. Initially, it behaved like a classic superluminous supernova, a fast rise to a sharp peak, followed by a slow decline. But then something happened that confounded scientists. After dimming for weeks, Assassin 15LH brightened again. This unexpected second peak was completely at odds with most known supernova behaviors. And while a few models, such as CSM, circumstellar medium, interaction or fallback accretion, might potentially explain such a resurgence, none of them matched the spectral data well enough to be convincing. Another reason the cause remains unclear is due to the conflicting interpretations of its host galaxy. Superluminous supernovae, SLSNA, especially the hydrogen-per type 1 variety, are typically found in young, low-mass, star-forming dwarf galaxies. These galaxies are rich and massive, short-lived stars that can explode as SLSNA. But Assassin 15LH's host was the opposite, a massive, passive galaxy with little or no star formation, and puzzlingly, one that likely harbored a supermassive black hole at its core. This raised a very different possibility. Was Assassin 15LH not a supernova at all, but a tidal disruption event, a star being ripped apart by a black hole? Initially, the TDE hypothesis seemed promising. TDEs also produce luminous, blue light curves and can mimic some features of supernovae. But again, the data didn't align neatly. There was a lack of hydrogen and helium emission lines, a typical signature of material being consumed by a black hole. Moreover, the shape of the light curve, the symmetry of the event, and the overall spectral evolution all drifted from what would be expected from even an extreme TDE. Another persistent mystery is the absence of definitive ejecta signatures. In a supernova, material from the exploded star expands outward at high velocities. This ejecta leaves telltale imprints in the spectrum, lines that shift over time as the debris cools and disperses. But Assassin 15LH never fully revealed those signs. Its spectrum remained curiously featureless and unchanging, leading to speculation that either the ejecta were highly unusual in composition, extremely hot and ionized for a prolonged time, or possibly being obscured or diluted by something unknown. Even more fundamentally, there's a theoretical limitation. Assassin 15LH stretches the known limits of energy generation. The Magnetar model, once a leading explanation, requires a newborn neutron star spinning at breakneck speed, faster than 1 millisecond per rotation, and possessing a magnetic field trillions of times stronger than Earth's. This theoretical Magnetar would need to inject its rotational energy into the supernova remnant with near-perfect efficiency to power such brightness. Yet this borders on physically implausible. At such extreme spin rates, the neutron star would likely collapse into a black hole or tear itself apart, and energy losses through gravitational waves or neutrino emission would sap much of its power before it could ever be translated into light. Alternative models have emerged: binary neutron star mergers, black hole fallback accretion, even entirely new classes of hypernovae or AGN flares masquerading as supernovae. But each of these comes with its own issues, inconsistencies, and unanswered questions. Moreover, the tools of observation themselves impose limits. While Assassin 15LH was detected across multiple wavelengths, optical, ultraviolet, and to some extent X-ray, there's still a dearth of information in the infrared and radio bands. These longer wavelengths can reveal dust formation, slow outflows, or interactions with surrounding gas. But in this case, such data were sparse or inconclusive. Without a complete electromagnetic fingerprint, the story remains frustratingly incomplete. Another factor is cosmic distance. Located 3.8 billion light-years away, Assassin 15LH is far enough that its light had to travel across more than a quarter of the universe's history to reach us. During that time, interstellar and intergalactic matter may have subtly altered the signal. While redshift adjustments help account for cosmic expansion, small absorption effects, scatterings, or lensing events could have affected our observations in subtle but significant ways. Finally, there's the chilling possibility that Assassin 15LH doesn't fit any current theory because it represents a new class of astrophysical phenomenon. Perhaps it is something entirely unaccounted for in existing models, a hybrid of supernova and TDE, a new type of black hole interaction, or a process that only occurs under rare galactic conditions. Perhaps it was a cosmic accident, an unrepeatable fluke born from an intersection of extreme physics we're just beginning to understand. The reason the cause remains unclear is not for lack of effort. It is because Assassin 15LH lies at the bleeding edge of what we know, and perhaps just beyond it. It taunts us not just with brightness, but with ambiguity. It is a puzzle piece that doesn't fit the jigsaw, no matter how we rotate it. And like many of the universe's deepest mysteries, it reminds us that science is not a collection of answers, but a process of relentless questioning. Assassin 15LH is a cosmic mirror, reflecting the limits of our understanding. It is a bright, silent messenger from a distant corner of the universe, whispering that the cosmos still holds secrets we haven't yet imagined. Assassin 15LH didn't just surprise astronomers. It threw a wrench into the very machinery of supernova theory itself. For decades, the study of supernovae has been guided by certain foundational principles. Stars die when they run out of fuel, the collapse of the core leads to a massive explosion, and this explosion follows patterns of energy release, light curves, and spectral behavior that, though varied, are generally predictable. But Assassin 15LH defied nearly all of that. What made it so disruptive was not just that it didn't fit existing models, it systematically broke them. Its brightness alone was the first and most immediate problem. The energy released during the peak of Assassin 15LH was so staggering that it far surpassed what is typically expected even in the most powerful known supernovae. If it truly was a supernova, then the energy source behind it had to be stronger than anything we'd ever observed, or even theorized. Supernova models are built around two main classes, core collapse and thermonuclear. Core collapse supernovae happen when massive stars, those more than about 8 times the mass of the Sun, run out of fuel and their cores implode under gravity. Thermonuclear supernovae, typically type I, occur in binary systems when a white dwarf accretes enough material from a companion to trigger runaway nuclear fusion. Both processes release a tremendous amount of energy, but they have clear limits. Even core collapse explosions, no matter how massive the progenitor star, typically produce a peak luminosity that's orders of magnitude below what was observed in Assassin 15LH. The Magnetar model, which involves a rapidly spinning neutron star with an intense magnetic field injecting energy into the supernova ejecta, had been introduced to explain superluminous supernovae, a relatively new subclass. But Assassin 15LH quickly revealed the cracks in this theory. The magnetar required to power such a luminous explosion would have to spin at the very edge of physical possibility, perhaps even beyond. We're talking about a spin period of less than a millisecond and a magnetic field strength greater than 10 superscript 1 Gauss. This combination is theoretically possible, but it is incredibly unstable. The energy injection would also need to occur with nearly perfect efficiency, an unrealistic requirement given the energy losses from neutrino emissions, gravitational waves, and other forms of radiation. Worse, the predicted spectrum and light curve from such a model didn't match the observations. The temperature stayed hotter for longer than expected, and the absence of hydrogen and helium in the spectra complicated things even further. Assassin 15LH also challenged assumptions about where supernovae occur. It was discovered in a massive, passive galaxy with little star formation. This is precisely the opposite environment where most superluminous supernovae are found. The prevailing theory had been that these kinds of supernovae require young, metal-poor stars in active star-forming regions, environments typically found in smaller, irregular galaxies. The fact that this explosion occurred in a massive, mature galaxy meant that either the progenitor star was extremely atypical, or that our understanding of superluminous events and their environments was incomplete, or both. These contradictions forced theorists to revisit and, in many cases, completely revise their models. Some proposed hybrid scenarios involving a magnetar embedded in a dense shell of circumstellar material that might have been ejected prior to the explosion. This would allow additional light to be generated as the ejecta plowed into the shell. But again, Assassin 15LH didn't show the expected signatures of such interaction, such as narrow emission lines from shocked gas. Others considered fallback accretion models, where after the core collapses, some of the stellar material falls back onto the newborn compact object, adding energy. But these too failed to account for the peculiar spectral features and the double-peak light curve behavior of Assassin 15LH. Then came even more speculative ideas. Some proposed that Assassin 15LH might be evidence of an entirely new class of explosions. Perhaps it was a quark nova, a hypothetical event where a neutron star further collapses into a quark star, releasing another titanic burst of energy. Or perhaps it was a direct collapse black hole formation event, where a massive star skips the traditional supernova explosion altogether and directly forms a black hole, ejecting energy in a completely new way. But none of these theories were grounded in observational evidence or simulation data sufficient to support them. One of the most disturbing implications of Assassin 15LH is that it highlights a potential blind spot in our astrophysical models. If such events are possible, even rare, then many of our conclusions about stellar evolution, the life cycle of galaxies, and the chemical enrichment of the universe may be incomplete. Our models are calibrated based on supernovae we can observe and understand. But what if we've only seen a subset of the possibilities? What if events like Assassin 15LH are only the tip of a much larger, more diverse iceberg of cosmic phenomena? This realization sparked a wave of new simulations and studies. Teams across the world began constructing more flexible models, exploring edge case physics, and factoring in variables previously thought to be negligible. Some even began using machine learning to comb through supernova data to detect anomalies that might hint at other Assassin 15LH-like events hidden in the noise. Another significant shift was in how astronomers now think about host galaxies. Assassin 15LH proved that rare, extreme events can occur even in galaxies that don't fit the textbook descriptions. This challenged long-held assumptions about how stellar mass, metallicity, and star formation rates influence cosmic explosions. The implication is profound. Any galaxy, regardless of its properties, might harbor the potential for cataclysmic, unpredictable outbursts. In the wake of Assassin 15LH, even the definition of what qualifies as a supernova is being reconsidered. Is a supernova solely the death throw of a single star? Or can we stretch the term to include hybrid events, black hole interactions, or multi-stage phenomena that defy our current categories? In essence, Assassin 15LH broke the mold. It wasn't just a rare event, it was a paradigm-breaking event. It forced scientists to rethink the boundaries of energy generation and stellar death. It made theorists reconsider which galaxies could host such phenomena. It opened the door to entirely new categories of cosmic events. And most of all, it reminded the scientific community that even with all our telescopes, satellites, and simulations, the universe still has the power to stun us into humility. The impact of Assassin 15 LH continues to ripple through astrophysics. Papers are still being written. New surveys have been designed with it in mind. And every time a supernova-like object is discovered, one question inevitably arises: is this another Assassin 15 LH? Or perhaps something even stranger? The power source of Assassin 15 LH remains one of the most confounding and captivating mysteries in astrophysics. When a star dies in a supernova, the energy we see, its brilliant glow across the cosmos, is typically powered by the immense release of gravitational energy during core collapse or by thermonuclear reactions in the stellar remnant. In most well-understood supernovae, the decay of radioactive nickel-56, which transforms into cobalt-56 and then into stable iron-56, is what sustains the light curve over time. This process is so reliable that astronomers use certain types of supernovae as standard candles to measure cosmic distances. But Assassin 15 LH didn't follow any of the expected energy rules. From the moment its light first reached Earth, it was clear this was no ordinary explosion. To reach a peak luminosity that was around 2.2 times 10 superscript 3 watts, nearly 570 billion times brighter than the Sun, Assassin 15 LH must have released an almost unthinkable amount of energy. The total radiated energy was estimated to be about 1.1 times 10 superscript 2 ergs, more than the combined energy output of all stars in our galaxy for an entire year. That figure is so staggering that it raised an immediate question: what could possibly be powerful enough to do this? Standard radioactive decay couldn't explain it. To produce that much light via nickel decay alone, Assassin 15 LH would have needed to synthesize about 30 solar masses worth of nickel-56. For context, even the most massive known supernovae only generate a few solar masses of nickel, and that's already pushing physical limits. 30 would require a progenitor star far beyond what we currently think is possible. Not to mention, such a huge amount of radioactive material would dramatically alter the spectral features of the explosion. Assassin 15 LH didn't show those features. It lacked the expected signatures in its spectrum, like iron group elements, and the broad absorption features typical of iron-rich ejecta. So if it wasn't radioactive decay, what then? One possibility that dominated early discussion was the Magnetar model. This model suggests that a newborn neutron star, a dense remnant left after a massive star collapses, could power the explosion if it were spinning rapidly enough and had a magnetic field trillions of times stronger than Earth's. In this scenario, the Magnetar's spin slows down over time, transferring rotational energy into the expanding debris and boosting its luminosity far beyond typical supernova levels. The Magnetar hypothesis has been successful in explaining other superluminous supernovae, SLSNA, particularly those classified as Type 1, lacking hydrogen lines in their spectra. But in the case of Assassin 15 LH, the numbers required to make the model work were alarmingly extreme. The neutron star would have needed an initial spin period of less than 1 millisecond, close to the physical limit for how fast any object of that mass can spin without tearing itself apart. Additionally, it would need a magnetic field strength exceeding 10 superscript 1 Gauss, stronger than what we observe even in the most powerful known magnetars. On top of that, nearly 100% of its rotational energy would need to be efficiently transferred into the supernova's ejecta without being lost to neutrinos, gravitational waves, or other leakage mechanisms. Even if those extreme conditions could theoretically be met, they still didn't account for Assassin 15 LH's full observed brightness. And worse, the light curve and spectra didn't entirely match Magnetar-powered models. Normally, a Magnetar-powered supernova would have a smoother, more gradual decline in brightness. But Assassin 15 LH didn't follow that curve. It dimmed, then unexpectedly brightened again, suggesting either a second energy input or a completely different mechanism altogether. Then came the circumstellar interaction models. In these, the explosion's energy is boosted when the expanding debris from a supernova crashes into a dense shell of gas that the star had expelled before it died. The collision produces shock waves, which convert kinetic energy into visible light. It's a well-known mechanism that explains many type Ion supernovae, which show narrow emission lines caused by this interaction. However, Assassin 15LH didn't show those emission features. If there was any circumstellar material, it must have been very thin or oddly distributed, nothing like the dense, hydrogen-rich shells seen in typical interaction-powered supernovae. Furthermore, Assassin 15LH's host galaxy didn't appear to be the kind of place where massive stars form and die violently, throwing off thick envelopes of gas beforehand. It was a massive, quiescent galaxy with little star formation. This meant it was unlikely the progenitor star had gone through the kind of erratic, mass-losing evolution needed for this model to work. As other models failed, some astronomers began considering fallback accretion. This is when some of the material that gets ejected in the initial explosion doesn't escape the gravitational pull of the remnant object, and instead falls back in. If that material falls onto a newly formed black hole, it could potentially generate enormous amounts of energy as it heats up in the accretion process. Fallback accretion has been proposed as a way to power faint, long-duration gamma-ray bursts, but applying it to a superluminous optical transient was a stretch, and once again, the light curve didn't match expectations. Fallback models also tend to be less luminous in the optical range and more energetic in gamma rays or X-rays. Assassin 15LH, by contrast, was optically dominant. As the usual suspects fell short, theorists moved deeper into the realm of speculation. Some proposed that perhaps Assassin 15LH wasn't a supernova at all but something more exotic. One of the most provocative ideas was that it might be a tidal disruption event, TDE, a star that strayed too close to a supermassive black hole and was torn apart by its tidal forces. The debris from the shredded star spirals around the black hole, heating up and emitting vast amounts of energy. This theory did have appeal, especially since the location of Assassin 15LH coincided with the nucleus of its host galaxy, where supermassive black holes are typically found. Moreover, the unusual light curve behavior, its unexpected dip and subsequent rebrightening, was more in line with some known TDEs than with supernovae. However, Assassin 15LH didn't exhibit the spectral features usually associated with TDEs, such as strong hydrogen and helium lines. It was also much more luminous than any TDE ever observed, by an enormous factor. The black hole in the host galaxy was also estimated to be very massive, around 100 million solar masses. At that size, it shouldn't be able to produce a visible TDE at all, because stars would be swallowed whole before they could be torn apart and heated up. There was even talk about quark novas, speculative events where neutron stars collapse further into quark stars, releasing vast amounts of energy in the process. Though entirely theoretical and unconfirmed, this concept illustrates how desperate the search became for a power source. Assassin 15LH had done what few astronomical discoveries manage. It broke the existing models so thoroughly that new physics had to be considered. Ultimately, what powers Assassin 15LH is still up for debate. It might be a once-in-a-universe supernova, powered by a magnetar with near-impossible characteristics. It might be a bizarre tidal disruption event, made visible by mechanisms we don't yet understand. Or it could be something entirely new, an event so rare and so powerful that we've never seen another like it. The search for its power source continues to this day. New observations, simulations, and theoretical papers are still being published. More superluminous events are being catalogued, and with each one, astronomers hope to find a twin, or at least a cousin, of Assassin 15LH that might finally unlock its secrets. And until we do, the power source of Assassin 15LH remains one of the most profound astrophysical puzzles of the 21st century, an enduring reminder that the cosmos still holds many secrets waiting to be illuminated. The Magnetar hypothesis emerged as one of the earliest and most promising explanations for the extraordinary brightness of Assassin 15LH. In a field where most stellar explosions follow familiar patterns and energy outputs, this particular theory attempted to account for what many other models could not: the sheer scale of the luminosity observed and the apparent absence of typical supernova signatures like abundant nickel decay or dense circumstellar material. It was bold, it was elegant, and it just might have worked if the physics hadn't pushed the envelope quite so far. At the heart of the Magnetar hypothesis is the idea that a newborn neutron star, formed from the collapsed core of a massive star, could act as a cosmic dynamo. If this stellar remnant had the right characteristics, namely, an incredibly fast rotation and an extraordinarily strong magnetic field, it could inject a vast amount of energy into the surrounding supernova ejecta. This process, in turn, would heat the expanding cloud of material and radiate light far more efficiently than the typical radioactive decay model could manage. So what exactly is a magnetar? A magnetar is a special kind of neutron star, which itself is already an extreme object. Neutron stars are what's left after a massive star, perhaps 10 to 25 times the mass of our Sun, ends its life in a supernova explosion. The core collapses under gravity until protons and electrons combine into neutrons, leaving behind an object no more than about 20 kilometers in diameter but with more mass than the Sun. This collapse concentrates angular momentum and magnetic field lines, sometimes resulting in spin rates of multiple times per second and magnetic fields so intense they could strip atoms apart from thousands of kilometers away. Magnetars go a step further. Their magnetic fields are among the most powerful in the universe, typically reaching 10 superscript 1 to 10 superscript 1 Gauss, trillions of times stronger than Earth's magnetic field. These magnetic fields are so intense that they can distort atomic structures, potentially causing starquakes on the surface of the neutron star. But more importantly, when coupled with rapid rotation, they can act as efficient engines for converting rotational energy into radiation. The magnetar hypothesis suggests that if assassin 15LH resulted from the collapse of an extremely massive star, it could have left behind such a rapidly spinning magnetar. The idea is that the magnetar was born with a spin period on the order of 1 millisecond, a rate so fast it's nearly at the theoretical limit before centrifugal forces would tear the object apart. At the same time, it would need a magnetic field at or above 10 superscript 1 Gauss. This combination allows for an enormous reservoir of energy, on the order of 10 superscript 2 ergs, to be injected into the supernova's expanding envelope over a relatively short period of time. This energy injection could keep the ejecta heated for an extended duration, resulting in a bright, prolonged light curve like the one observed in assassin 15LH. It also sidesteps the need for massive amounts of radioactive nickel, which the spectrum of assassin 15LH notably lacked. From a purely energetic standpoint, a magnetar engine could, in theory, explain how assassin 15LH reached such peak brightness and maintained it longer than typical supernovae. In modeling studies, scientists used variations of the magnetar-powered supernova framework to recreate the light curve of assassin 15LH. Some of these attempts were quite successful, under certain conditions. The required magnetar had to be almost unreasonably fast and efficient, converting its rotational energy to radiant energy with nearly 100% effectiveness. The models assumed that little to no energy would be lost to gravitational waves, neutrinos, or other forms of dissipation, an optimistic assumption, to say the least. This led to a number of fascinating theoretical implications. If such magnetars could exist, they would be among the most extreme objects in the known universe. Their very existence would challenge our understanding of neutron star formation and stability. They would skirt the line between physics and theoretical extremity, existing in a realm we had not yet observed directly. And most importantly, they would offer a clean, elegant way to explain superluminous supernovae like assassin 15LH without needing to invoke more exotic or controversial mechanisms. The magnetar hypothesis also fits within a broader pattern in recent astrophysical research. Several other superluminous supernovae, including SN 2005 AP and SN 2010 GX, have shown characteristics that seem to match a magnetar-powered origin. The idea has gained traction as a plausible explanation for a variety of unusually bright and long-lasting cosmic events. In some cases, it has even become the default fallback model when more traditional explanations fail. However, assassin 15LH isn't just any superluminous supernova. It's the brightest ever recorded, and with that distinction comes a degree of scrutiny that few models can survive. As promising as the magnetar hypothesis was, it soon began to unravel under the weight of the data, something that will be explored more in the next segment. But for a time, it stood as the leading candidate, offering a mechanism that was at least physically plausible, if not fully satisfying. Still, its emergence as a viable explanation underscores something profound about modern astrophysics. We're often operating at the edge of our understanding, using the tools of theory and observation to stretch the boundaries of the possible. The Magnetar model may not have all the answers, but in a universe that continues to surprise us with its scale and strangeness, it remains one of the best windows into what might be happening when the cosmos decides to outshine itself. Despite its early promise, the Magnetar hypothesis began to show serious cracks when astronomers took a closer look at what was actually required for such a scenario to explain Assassin 15LH. The physics behind the Magnetar-powered supernova model may have been elegant in theory, but when that theory was put under the microscope of extreme data from the most luminous transient ever observed in the cosmos, its limitations became glaringly apparent. As time passed and observations continued, the problems with the Magnetar model multiplied, revealing that even one of the universe's most extreme known engines might not be powerful enough to account for what Assassin 15LH had achieved. First and foremost, there is the problem of energy limits. The total radiant energy emitted by Assassin 15LH was estimated to be over 2 times 10 superscript 2 ergs, an absolutely staggering figure. To put that into perspective, this is about 10 times more than the total energy the Sun will emit over its entire 10 billion-year lifespan, concentrated into just a few months. That number approaches the maximum theoretical energy budget of a magnetar formed under the most extreme conditions. A typical magnetar, born with a spin period of around 1 millisecond and a magnetic field of 10 superscript 1 superscript 1 Gauss, can potentially release a similar magnitude of energy, but only if 100% of its rotational energy is somehow converted into electromagnetic radiation without significant losses. And this is where the first major inconsistency arises. No physical system is 100% efficient. Some of the energy will inevitably be lost as gravitational waves, neutrino emission, and thermal dissipation. Additionally, not all the energy released by the magnetar will necessarily be coupled efficiently to the expanding ejecta of the supernova. If even a fraction of the energy is diverted or lost, the remaining budget quickly becomes insufficient to explain Assassin 15LH's brightness. Another issue lies in the timing and shape of the light curve. When astronomers attempted to model the rise and fall of Assassin 15LH's light curve using a magnetar-based energy injection model, they found that it required incredibly precise tuning of the magnetar's properties. The spin-down rate, magnetic field strength, and initial spin period all had to be fine-tuned to within razor-thin margins. While this is not impossible, it is statistically improbable, meaning that if Assassin 15LH really were powered by a magnetar, it would have to be an extraordinarily rare and finely balanced configuration. Moreover, the re-brightening event seen in Assassin 15LH, the strange dip and subsequent rise in brightness several weeks after its peak, is especially difficult to reconcile with the magnetar model. In typical magnetar-powered supernovae, the energy input from the neutron star steadily declines as the rotation slows, leading to a fairly predictable drop-off in luminosity. The kind of secondary brightening observed in Assassin 15LH would require either a second phase of magnetar activity, for which there is no clear physical mechanism, or an interaction with external material, which was not supported by the spectral data. Then there's the problem of spectral features, or rather, the lack thereof. In a supernova energized by a magnetar, one would typically expect the high-energy radiation from the neutron star to leave some sort of imprint on the surrounding ejecta, such as ionization lines, changes in opacity, or other spectral evolution over time. But Assassin 15LH remained unusually featureless across multiple wavelengths. This spectral blandness doesn't support a high-energy internal engine operating with ferocious power, unless it's doing so in an unusually shielded or non-interacting way, again requiring a very precise and speculative arrangement. Additionally, the location of the explosion further complicates the magnetar narrative. Assassin 15LH occurred near the center of a quiescent, massive, old galaxy, one not known for current or recent star formation. Magnetars, on the other hand, are usually the remnants of massive, short-lived stars, which are most commonly found in galaxies rich in gas and ongoing star formation. The discrepancy between the expected environment of Magnetar births and the actual location of Assassin 15LH raises significant doubts. If no massive stars were forming in this region for hundreds of millions of years, then what massive star could have recently exploded to form a Magnetar in the first place? Another complicating factor is the lack of circumstellar material. Some researchers propose that a Magnetar engine might interact with a dense surrounding medium, converting kinetic energy into light and enhancing brightness. However, extensive follow-up observations, including ultraviolet and X-ray studies, found no evidence of such material. Without this additional amplification mechanism, the burden falls entirely on the Magnetar itself to explain the energy output, which, as discussed, stretches credibility. Also of note is that the timescale of energy deposition doesn't quite match. Magnetar-powered models tend to predict a faster rise and decline than what was observed. Assassin 15LH rose more slowly and declined more gradually than most modeled outputs for Magnetar-powered supernovae. Attempts to stretch the model to match this light curve often require assumptions that push neutron star physics to the limits: rotational speeds near breakup, magnetic fields so strong that they risk destabilizing the star, and mass loss scenarios that don't match known progenitor systems. And finally, there is the absence of corroborating observational evidence. No clear detection of a neutron star or Magnetar remnant has been observed in the aftermath of Assassin 15LH. Of course, this doesn't rule it out. The object is billions of light-years away, but it adds to the cumulative uncertainty. A good scientific model not only explains the observed data but also fits into a broader context supported by multiple lines of evidence. In this case, the Magnetar hypothesis explains the brightness only if a number of extraordinary conditions are assumed, and even then, it struggles to align with the spectrum, the light curve shape, the rebrightening, and the galactic environment. This isn't to say the Magnetar model is completely invalid. It remains one of the few semi-plausible options. But it's clear that Assassin 15LH pushes this explanation to its breaking point. The required parameters lie so far into the tails of theoretical distributions that many scientists began to question whether a completely different mechanism, one not dependent on the traditional supernova framework, might be at play. A Magnetar may be one of the most powerful engines in the universe, but even it might not be enough to explain the brightest flash of light we've ever seen. One of the most tantalizing explanations that emerged in the wake of the Magnetar hypothesis struggles was the possibility that Assassin 15LH might not have been a supernova at all, but something else entirely. Specifically, astronomers began seriously considering whether this immense cosmic flare might have been the result of a tidal disruption event, or TDE, a star wandering too close to a massive black hole and being ripped apart by gravitational forces so intense that it defies comprehension. This theory wasn't just an act of scientific desperation, it was grounded in real astrophysical models, and the clues began to align in curious, unexpected ways. To understand how a black hole might produce something like Assassin 15LH, we need to explore what actually happens during a tidal disruption. When a star approaches a supermassive black hole, particularly within the tidal radius, the difference in gravitational pull between the star's near side and far side becomes so extreme that the star is pulled apart in a dramatic and violent process. The star is essentially spaghettified, stretched and shredded into a stream of hot plasma. Some of this matter is flung into space, but a significant fraction falls back toward the black hole, forming an accretion disk that heats up to extreme temperatures and radiates immense energy, often in ultraviolet and X-ray wavelengths. The result is a transient event so luminous that it can rival, or even outshine a typical supernova. At first glance, this explanation for Assassin 15LH seems far-fetched. TDEs are typically observed in smaller galaxies with active black holes, and they often emit radiation more strongly in the X-ray spectrum, not the optical and ultraviolet ranges where Assassin 15LH was most dominant. However, Assassin 15LH challenged these conventions in almost every regard. First, its location, right in the heart of a massive, passive galaxy, lined up disturbingly well with what one might expect from a dormant supermassive black hole just waiting to awaken. Follow-up observations, particularly those from the Hubble Space Telescope, found that the event had occurred within mere hundreds of parsecs from the galactic nucleus, extremely close to where a central black hole would reside. This raised eyebrows for another reason. Supernovae, even the most luminous ones, are almost never found in the central regions of massive galaxies. That's because the dense galactic core typically hosts older, low-mass stars, not the massive, short-lived ones that give rise to magnetars or other exotic stellar deaths. The environment simply didn't fit the standard stellar collapse model. But it did fit a TDE. Adding to the intrigue was the strange light curve behavior. Assassin 15 LH showed an initial brightening, followed by a surprising dip, and then a secondary rebrightening phase, a rare pattern not easily explained by supernova models but sometimes seen in TDEs. In some simulations of tidal disruption events, material torn from the star takes time to fall back toward the black hole. The rate at which this debris accretes, and thus the luminosity of the flare, can fluctuate depending on the distribution of stellar material, the spin of the black hole, and relativistic effects near the event horizon. This could potentially explain the observed dip and rise in Assassin 15 LH's light output. Yet, the TD theory was not without its problems. The most glaring one involved scale. TDs typically occur around black holes with masses between 10 and 10 solar masses. If the black hole is too massive, above roughly 10 solar masses, the tidal radius lies within the event horizon, meaning that a star would be swallowed whole without the telltale flare. This is called the direct capture regime. And here's the twist. The host galaxy of Assassin 15 LH appeared to be so massive that, based on galaxy black hole scaling relations, its central black hole might be too large to permit observable tidal disruptions. In other words, any star that ventured close enough to be torn apart would likely disappear silently into the black hole, never producing the spectacular light show we observed. Some theorists tried to resolve this paradox by proposing that the black hole at the center of this galaxy might not be non-rotating. If the black hole were rapidly spinning, a so-called Kerr black hole, then the tidal radius could actually lie outside the event horizon even at higher masses. This would allow a TDE to occur in a more massive system. But this idea adds complexity and speculation to the model. It requires assumptions not just about the black hole's mass, but also its spin, orientation, and the specific trajectory of the unfortunate star. Another wrinkle came in the spectral characteristics of Assassin 15 LH. Typical TDEs show broad emission lines, often of hydrogen or helium, produced as the accreting material emits light. But Assassin 15 LH's spectrum was anomalously featureless, making it hard to compare to other well-studied tidal disruption flares. Some of the most persuasive arguments for TDEs rest on spectral fingerprints, and those were conspicuously absent here. Still, even these contradictions weren't enough to discard the black hole scenario outright. A few astronomers proposed a novel kind of TDE, perhaps one involving a highly stripped or compact star, like a white dwarf or helium star, that wouldn't produce the usual spectral features. Alternatively, if the viewing angle was just right, or the accretion disk structure unusually opaque, the emission lines might have been obscured from view. Furthermore, the energy budget of Assassin 15 LH remained a good match for accretion-powered processes. Theoretical models suggest that accreting just a fraction of a solar mass onto a supermassive black hole can release more than 10 superscript 2 ergs of energy, the same ballpark as the total output observed. So while the Magnetar hypothesis struggled to produce enough energy, the black hole explanation at least had the raw power needed to explain the flare. In fact, several researchers published models showing that an intermediate mass black hole, or a rapidly spinning supermassive black hole, could indeed generate the observed luminosity profile if the star was disrupted in a precise, finely tuned manner. These models incorporated relativistic effects, complex fallback rates, and evolving disk geometries to produce light curves resembling what we saw in Assassin 15 LH. There was even a suggestion that Assassin 15 LH could represent a new hybrid class of events, something between a supernova and a tidal disruption event. Perhaps a massive star exploded near a central black hole, and its material was later accreted, amplifying the luminosity to extreme levels. Or maybe it was an entirely novel kind of transient, a cosmic chimera for which we currently have no established category. The black hole scenario may not answer every question, but it offers a compelling and powerful framework that aligns well with some of Assassin 15LH's most unusual traits: its location, its longevity, its brightness, and even its mysterious light curve behavior. It's one of the few hypotheses that doesn't require breaking the laws of physics to match the energy output. Still, astronomers are cautious. Without clearer spectral data or a recurrence event to provide more information, the black hole explanation remains one piece of a much larger puzzle. Assassin 15LH continues to exist in that gray space between known categories, daring scientists to come up with new physics, new categories, or perhaps a radical rethinking of how we understand the most luminous events in the cosmos. Despite the compelling narrative surrounding the black hole scenario for Assassin 15LH, the theory is far from watertight. In fact, as astronomers dug deeper into this interpretation, more cracks began to appear, especially when considering the type of galaxy that hosted this extraordinary event. While the black hole model checks certain boxes, like energy budget and location in the galactic nucleus, it simultaneously raises serious red flags that make it just as problematic, if not more so, than the Magnetar hypothesis it aimed to replace. To begin with, one of the most critical inconsistencies arises from the host galaxy itself. Assassin 15LH erupted in the center of a massive, quiescent, elliptical-type galaxy, characterized by old stellar populations, low star formation rates, and a general lack of activity. This kind of environment isn't just unusual for a tidal disruption event, TDE. It's almost a complete contradiction of the environments where TDEs are most often observed. Traditionally, TDEs are discovered in low-mass, star-forming, or post-starburst galaxies, places where there is still some degree of nuclear activity and a plentiful supply of stars drifting near the central supermassive black hole. The assumption here is straightforward. The more dynamic the stellar environment, the higher the likelihood of a star being gravitationally disturbed and drawn too close to the black hole's tidal radius. But Assassin 15LH defies this expectation entirely. Its host galaxy is passive, showing no signs of recent starburst activity or a high central stellar density, both of which would be prime indicators for a TDE-friendly environment. The central region of such an evolved elliptical galaxy is populated mostly by ancient, low-mass stars that aren't typically disrupted in the dramatic fashion required to produce a flare of Assassin 15LH's magnitude. This brings into question how likely it is for a random star to wander close enough to a central black hole in such a dormant system. The odds are extremely low. Additionally, there is the problem of galactic black hole mass estimates. Based on the host galaxy's size and mass, scaling relations suggest that the central black hole could be in the range of several 100 million to possibly a billion solar masses. At those sizes, the tidal radius for a Sun-like star would actually lie within the black hole's event horizon. In simple terms, a star would be swallowed whole before it could be shredded and produce a flare visible to the outside universe. This is known as the direct capture regime, and it's a fundamental barrier to observing TDEs around extremely massive black holes. Some theorists tried to bypass this by proposing that the central black hole could be rapidly spinning, which, due to relativistic effects, would allow the tidal radius to move slightly outward, just far enough to permit a tidal disruption to occur outside the event horizon. But this is a very specific and fine-tuned condition. Not only do we need to assume the black hole is spinning fast enough, but also that the disrupted star followed just the right orbital trajectory to allow a partial disruption in an extremely narrow, Goldilocks, zone of conditions. This level of specificity strains the credibility of the model and relies on numerous assumptions that cannot currently be confirmed. Even the radiation signature poses a conundrum. TDEs, when they do occur, often produce strong X-ray emissions as material heats up in the accretion disk before falling into the black hole. Assassin 15LH, on the other hand, emitted primarily in the optical and ultraviolet spectra, with no prominent X-ray signature detected. This discrepancy is hard to reconcile, even with generous assumptions about viewing angles, obscuring matter, or disk geometry. If the emission was reprocessed by a thick layer of gas or dust, we'd expect to see some telltale signs of that in the spectra, and yet those features were notably absent. Another piece that doesn't quite fit is the shape and timing of the light curve. While some TDEs have exhibited complex light curves with dips and secondary peaks, Assassin 15LH's behavior was especially erratic and prolonged. The secondary brightening phase that occurred about 2 months after the initial flare is not something that TDE models can easily reproduce. The timing, duration, and magnitude of this second peak are all outliers when compared to known tidal disruptions. Furthermore, the total energy output over the duration of the event was immense, exceeding 2x10 superscript 2 ergs, nearly 10 times more than most well-characterized TDEs. Even accounting for highly efficient accretion processes and optimal geometry, it remains difficult for standard TDE models to account for this much radiated energy without invoking additional, speculative mechanisms, such as jet formation or unusually high fallback rates. Yet, Assassin 15LH did not show any evidence of relativistic jets, high-speed outflows that are often seen in the most luminous TDEs, and which help explain their power. This leaves the black hole explanation in a precarious position. On one hand, it fits certain elements quite well: the proximity to the galactic center, the longevity of the event, and the sheer magnitude of the energy output. But on the other, it falters due to the nature of the host galaxy, the apparent mass of the black hole, the spectral profile, and the strange morphology of the light curve. It's a puzzle where every piece that seems to click in place causes 2 others to shift uncomfortably out of alignment. There's also the larger issue of statistical expectation. If Assassin 15LH is truly a TDE occurring in such an unlikely environment, it would imply that our understanding of where and how TDEs occur is fundamentally flawed, or that this event was a once-in-a-galactic lifetime fluke. Neither scenario is particularly satisfying from a theoretical standpoint. It would suggest that either our entire model of stellar dynamics and galactic cores needs to be revised, or that Assassin 15LH represents an outlier so extreme that it tells us very little about the broader population of similar events. That said, this doesn't render the black hole theory useless. Rather, it underscores just how rare and exotic this event truly is. The inconsistencies serve to highlight that if Assassin 15LH is a TDE, then it must be a new subclass, one that challenges not just what we know about supernovae and black holes, but also about the environments in which these cataclysms can occur. This blend of clues and contradictions has left astronomers in a state of cautious curiosity. They've recognized that the black hole scenario might be partially correct, but perhaps missing a key ingredient. Some have even proposed that Assassin 15LH may not be solely a supernova or a tidal disruption event, but rather a hybrid phenomenon, involving aspects of both, or something entirely unclassified. As such, Assassin 15LH remains a case study in the limitations of current astrophysical models. It stands as both an opportunity and a challenge, a cosmic Rosetta Stone that, once deciphered, could unlock a deeper understanding of the universe's most extreme energies, or perhaps even introduce us to a new class of transient event altogether. The Hubble Space Telescope played a pivotal role in peeling back the layers of mystery surrounding Assassin 15LH, offering insights that ground-based telescopes simply couldn't reach. In a situation where theories collided and models strained under the weight of uncertainty, Hubble became a crucial arbiter, its unparalleled resolution and precision enabling astronomers to probe not just the afterglow of the explosion, but the very heart of the galaxy it came from. If Assassin 15LH was an enigma, then Hubble was the magnifying glass scientists used to examine every fine detail. Shortly after the discovery of Assassin 15LH in June 2015 and the subsequent realization that it was not just another supernova, the scientific community turned to Hubble to provide clarity, literally. Observing in both ultraviolet and optical wavelengths, Hubble gave researchers the high-resolution imagery needed to zoom in on the event's precise coordinates. What it revealed first and foremost was the exact location of the explosion, a piece of information that helped eliminate several competing theories and simultaneously gave rise to new ones. One of Hubble's early contributions was pinpointing assassin 15LH to within less than 200 parsecs of the galactic nucleus, a distance astonishingly close to the central region of the host galaxy. This precision was critical because it nudged the needle toward the tidal disruption event hypothesis, which typically involves a star being torn apart by the intense gravity of a supermassive black hole near the galaxy's core. Prior to Hubble's data, there was ambiguity about whether assassin 15LH was an off-nucleus event, possibly a supernova located in a spiral arm or peripheral region. Hubble's sharp imaging dissolved that uncertainty. But the revelations didn't stop there. The Hubble Space Telescope also provided valuable data about the host galaxy itself, exposing characteristics that further complicated the puzzle. As the data streamed in, astronomers realized they weren't looking at a young, active galaxy, the kind typically associated with star formation, massive stellar deaths, and even tidal disruption events. Instead, they were staring into the calm, subdued face of a massive elliptical galaxy, one that appeared to be in the twilight years of its cosmic life. Hubble's images revealed a galaxy devoid of young blue stars, lacking the signature dust lanes and glowing regions of star birth that mark more youthful galaxies. It was the kind of environment where time has slowed to a crawl, a galactic graveyard, not a stellar nursery. This posed a significant contradiction to the prevailing models of both superluminous supernovae and TDEs, which are generally seen in more active and dynamic galaxies. It raised an important question: what was a record-breaking cosmic explosion doing in such an old, quiet place? Moreover, the morphology captured by Hubble suggested the galaxy had a dense, spheroidal bulge with no signs of recent galactic mergers or disruptions, another critical piece of the puzzle. If a galaxy had recently merged with another, it might have introduced chaotic gravitational interactions that could throw stars toward the central black hole, triggering a tidal disruption. But here, the evidence of such recent activity was strikingly absent. Hubble seemed to say, nothing about this host galaxy makes sense in the context of what we think causes assassin 15LH-like events. To quantify these observations, scientists used Hubble's data to estimate the galaxy's stellar mass, coming in at around 2 times 10 superscript 1 solar masses, which is massive by any standard. From this, they inferred the mass of the central black hole, which likely sits in the range of 100 million to 1 billion solar masses. As previously discussed, that size of black hole presents serious problems for tidal disruption models. According to classical physics, a black hole that large should swallow stars whole without producing the visible flare we associate with a TD. Here, Hubble did more than take a snapshot. It put boundaries on the debate, essentially saying, if this was a TDE, it had to break the rules. The galaxy simply didn't fit the profile. It wasn't chaotic or active enough. The black hole was likely too large, and the stellar population too old and cold for such a spectacular event to occur naturally. These constraints forced theorists to stretch the boundaries of existing models, suggesting possible black hole spin effects, unconventional types of stars, or even proposing entirely new classes of galactic nuclear events. Beyond the physical characteristics of the host, Hubble also tracked the evolution of the transient light over time. Its sensitive instruments monitored how the brightness of assassin 15LH changed across multiple wavelengths, revealing the curious rebrightening phase months after the initial explosion. Ground-based telescopes had already noticed the anomaly, but Hubble's precision allowed astronomers to trace the energy output and shape of the light curve with far greater fidelity. These UV and optical light curves further deepened the mystery, as they deviated from any known supernova or TDE model in both duration and intensity. Hubble's ultraviolet observations, in particular, were a goldmine. The UV spectrum is crucial when studying high-energy events, and assassin 15LH emitted unusually strong ultraviolet radiation, far stronger than most supernovae. These measurements suggested the presence of extreme temperatures and energetics well beyond the capabilities of standard explosion mechanics. And yet the lack of X-ray emissions, a common trait in tidal disruption events, added a strange counterbalance. The UV was telling one story, but the silence in X-rays was telling another. Hubble provided a clear image, but not a simple interpretation. Even more intriguingly, Hubble's findings have since become a benchmark for future transient events. The data collected have been stored, reanalyzed, and compared against new, similarly mysterious outbursts. In that sense, Hubble has not just illuminated Assassin 15 LH, but also laid the foundation for investigating the next generation of cosmic anomalies. Its high-resolution images and light curves now serve as a cosmic reference guide, helping scientists distinguish between categories of explosive phenomena, be they supernovae, TDEs, or something entirely new. As a result, Hubble's role transcends mere observation. It has become a litmus test for astronomical models. It proved that the environment around Assassin 15 LH was fundamentally inconsistent with what we thought we knew. It sharpened the outlines of the mystery while simultaneously making the core question more profound. How can something so luminous, so energetic, and so bizarre happen in a place so seemingly uneventful? While Hubble didn't solve the mystery of Assassin 15 LH, it did exactly what the best scientific instruments are supposed to do. It refined the problem. It ruled out simplistic answers, strengthened the case for more nuanced interpretations, and emphasized just how little we truly know about the most extreme forces in our universe. Thanks to Hubble, we see the puzzle more clearly, but that clarity only deepens the enigma. In the wake of Assassin 15 LH's blinding emergence onto the cosmic stage, the astronomical community activated a diverse ensemble of telescopes and observatories to study it across as many wavelengths as possible. The detection by OSIS-SN had already guaranteed interest, but the initial analysis suggesting an unprecedented brightness, over 570 billion times more luminous than our Sun, compelled observatories around the world and in orbit to pivot their eyes toward this strange light. While Hubble may have provided the most detailed imaging of its host galaxy, the broader understanding of Assassin 15 LH was truly a collaborative symphony of observational power, with a number of other telescopes contributing invaluable data to unravel the mystery. Among the first to join the investigation was the Swift Observatory, a NASA space telescope specially designed to monitor gamma-ray bursts and other high-energy events. Swift's ultraviolet/optical telescope, UVOT, and X-ray telescope, XRT, played crucial roles in tracking Assassin 15 LH. The UVOT offered extended coverage of the supernova's intense ultraviolet emissions, allowing astronomers to monitor how the UV brightness evolved in the weeks and months after the initial detection. Swift was instrumental in confirming the unusual longevity and thermal behavior of Assassin 15 LH's light. Perhaps even more telling was Swift's XRT, which found a near-total absence of X-ray emissions, something incredibly strange if the event were a tidal disruption caused by a supermassive black hole, since such events typically produce strong X-ray flares. This discrepancy tilted the scale away from the black hole theory for a time, although it wouldn't be the final word. Another powerful player in this effort was PanSTARRS, the Panoramic Survey Telescope and Rapid Response System. Based in Hawaii, this wide-field optical survey system routinely scans the sky and was able to provide supporting photometric data for Assassin 15 LH. Although it didn't detect the supernova independently, PanSTARRS contributed by supplying archived images of the region prior to the explosion, confirming that there was no previous activity in that location. This helped rule out periodic or repeating variables, cementing Assassin 15 LH as a unique, one-time event. More importantly, PanSTARRS high-cadence imaging allowed it to help track the object's light curve, which revealed that mysterious dip and subsequent rebrightening, an anomaly that few supernova models could explain. Complementing these observations were the ground-based Los Cumbres Observatory Global Telescope Network, LCOGTN, a global array of robotic telescopes designed to provide continuous monitoring of transient phenomena. Their flexible scheduling and round-the-clock coverage from multiple longitudes made them ideal for monitoring the long-term evolution of Assassin 15 LH's brightness. They contributed crucial time series data that helped create a detailed light curve, showcasing both the initial decline and the baffling second rise in luminosity. This extended optical coverage provided one of the clearest records of how the event evolved, highlighting just how atypical it was compared to other supernovae or known transient events. Also instrumental were the European Southern Observatory's telescopes, particularly those at La Silla and Parenal, which were used for spectroscopic follow-up observations. By breaking down the light from Assassin 15LH into its constituent wavelengths, astronomers hoped to uncover the chemical fingerprints that might tell them what materials were being ejected, at what speeds, and under what physical conditions. However, the results only added to the mystery. The spectra lacked the strong hydrogen or helium lines typical of many supernovae, pushing scientists toward classifying it as a Type I superluminous supernova, at least initially. Then came the Southern African Large Telescope, SALT, and the Magellan telescopes in Chile, both of which conducted high-resolution spectroscopy and photometry. These observations allowed scientists to probe deeper into the host galaxy's characteristics, supporting Hubble's findings that the galaxy was massive, old, and passive, totally out of place for this kind of violent event. SALT also played a key role in capturing the early spectral evolution of Assassin 15LH, offering more clues that it didn't fit neatly into any known category. Infrared observations were attempted using facilities like the Spitzer Space Telescope and various ground-based infrared telescopes. While Assassin 15LH was mostly studied in the optical and UV bands, the infrared observations aimed to detect any potential dust formation or reprocessing of the explosion's light by surrounding material. These studies turned up no significant infrared echo, another curious feature. If Assassin 15LH had occurred in a dust-rich environment, or if its explosion had illuminated surrounding material, scientists might have seen infrared signatures weeks or months after the explosion. The silence in this wavelength further deepened the mystery. Even radio telescopes like the Very Large Array, VLA, were tuned in to search for emissions that might have hinted at a shockwave or interaction with the surrounding medium, common in many types of supernovae and TDEs. But again, the data showed nothing substantial. The absence of radio waves ruled out powerful jets or blast waves that usually accompany relativistic outflows, which are often seen in energetic TDEs or long-duration gamma-ray bursts. This left scientists scratching their heads yet again. How could something so bright be so silent across so many wavelengths? In addition to these major players, countless other observatories across the globe contributed smaller, but still valuable, datasets to the campaign. Observatories in Spain, Australia, and the United States each contributed time on their instruments, from mid-size reflectors to high-powered spectrographs. It was a truly international, multi-wavelength collaboration involving dozens of institutions and hundreds of astronomers all trying to make sense of this cosmic anomaly. What became clear through this chorus of telescopes was that no single wavelength told the full story. Optical telescopes observed a light curve that was both astonishing and baffling. Ultraviolet telescopes revealed intense, prolonged emissions, hinting at extreme heat and energy. X-ray and radio observatories found nothing, even when something should have been there. Spectroscopic data failed to yield the elemental signatures that would have confirmed any known model. Every telescope contributed a puzzle piece, but the full picture still refused to take shape. Despite the intense scrutiny, Assassin 15LH remained frustratingly enigmatic. Each observatory confirmed its uniqueness, none could fully explain it. But together, they helped rule out conventional models, force the scientific community to refine its definitions of supernovae and TDEs, and pave the way for entirely new theories. It was not just one observatory that illuminated this phenomenon, it was the collective eye of humanity, turned toward a cosmic riddle that still defies resolution. When we think about the spectacle that was Assassin 15LH, it's natural to wonder what might happen if such a phenomenal event were to occur not billions of light years away, but somewhere much closer, perhaps in our own galaxy. It's a question that draws both awe and a tinge of existential curiosity. While Assassin 15LH unfolded at a safe distance of about 3.8 billion light-years, if a similar supernova or whatever cosmic mechanism powered it were to erupt within the Milky Way, the consequences, both visible and potentially harmful, could be extraordinary. Let's start with the visual impact. Assassin 15LH was calculated to be around 570 billion times brighter than the Sun. If an object of comparable luminosity exploded somewhere even as far as the other side of our galaxy, say, 30,000 light-years from Earth, it would easily outshine all other stars in the night sky. It could rival, or even surpass, the brightness of the full moon. For weeks, possibly months, this single point in the sky would dominate both night and even portions of daytime visibility. Imagine looking up and seeing an unfamiliar, intense light burning with steady power at the center of the night, casting shadows, disrupting biological circadian rhythms, and becoming the subject of global awe and media frenzy. Depending on the spectral characteristics, such an event could emit strongly in ultraviolet or X-rays, potentially leading to elevated levels of ionizing radiation reaching Earth's upper atmosphere. However, at such distances, Earth's atmosphere would likely provide adequate shielding against anything catastrophic. The real danger would arise if such an event occurred much closer, within a few thousand light-years. While rare, supernovae have been known to occur in the Milky Way roughly every 50 to 100 years, though most are obscured by dust or happen on the far side of the galactic core. If assassin 15LH-like phenomena involve unknown or exotic physics, say, a new class of hypernova or an especially violent form of tidal disruption, the energy profiles might include particles or radiation unlike those we've encountered before. Some theorists speculate that if the explosion emitted gamma rays in a focus beam, and Earth happened to lie in the path of that jet, the consequences could range from atmospheric ozone depletion to a potential mass extinction event, depending on proximity. Thankfully, assassin 15LH did not exhibit the narrow, directed beams seen in gamma ray bursts, which are considered far more dangerous if pointed directly at Earth. There is also the gravitational implication to consider. If assassin 15LH was a tidal disruption event involving a supermassive black hole, such a process occurring in the Milky Way would almost certainly require the involvement of our own galactic center, Sagittarius A. That black hole is largely dormant today, but if it were to become active in such a dramatic and luminous way, it could alter the environment near the galactic core significantly. Fortunately, the Sun is situated in a relatively quiet neighborhood, about 26,000 light-years from the center, so even a large outburst at Sagittarius A would be unlikely to directly endanger Earth. However, the event would likely flood the galactic environment with energy, cosmic rays, and radiation that could have long-term impacts on the heliosphere and perhaps even the climate. It's important to note that assassin 15LH's peak brightness wasn't the result of narrow beam emissions like gamma ray bursts but rather a broad, luminous swell. If such a light were unleashed close to us, the visual effects would be awe-inspiring, but perhaps not dangerous unless the event occurred within 100 to 1,000 light-years, a relatively close range in galactic terms. Within that sphere, Earth could experience direct consequences, from radiation exposure to possible biological effects on the surface of the planet. Now let's entertain the hypothetical scenario where a superluminous event of this scale happened within just a few dozen light-years. At that distance, Earth would be at risk of a significant dose of high-energy radiation. The atmosphere might be stripped of protective ozone layers, increasing ultraviolet exposure from the sun. Mutations in DNA, disruptions in the food chain, and global ecological stress could follow. This has been proposed as a mechanism for past extinction events, such as the one around 450 million years ago, possibly linked to a gamma ray burst or other stellar explosion. But the probability of such a cataclysmic event happening close to us is vanishingly small. Superluminous supernovae are already incredibly rare, and the conditions necessary for them to form, particularly involving massive, short-lived stars, are less common in our part of the galaxy. Our Sun is a relatively small, middle-aged star in a quiet spiral arm. The massive, unstable stars that tend to give birth to the kinds of supernovae assassin 15LH might represent are found in denser, more active regions of star formation. Even if the true nature of assassin 15LH is a tidal disruption event, the presence of a dormant supermassive black hole in our stellar neighborhood is unlikely. The known black holes near us are either of stellar mass or relatively inactive. Still, the prospect remains an eerie one. The sudden appearance of a celestial object that bathes the planet in unnatural light, drawing eyes from every corner of the Earth, would no doubt be interpreted with alarm, wonder, or both. It would redefine the night sky, and spark perhaps the largest scientific mobilization since the discovery of gravitational waves. Astronomers would rush to repoint satellites and observatories. News outlets would run non-stop coverage. Theories would fly about what exactly was happening. In the best-case scenario, it would be a dazzling, once-in-a-civilization spectacle, safe but overwhelming. In the worst-case scenario, it might pose a real threat to life on Earth. The truth is that cosmic events on the scale of Assassin 15 LH remind us just how dynamic and powerful the universe is, and just how small we are in its ever-unfolding drama. We live under a quiet sky, but that quiet is punctuated, from time to time, by explosions so massive they defy language, reason, and physics as we understand it. One only hopes that if we ever witness such a phenomenon up close, it will be from a safe distance, one where awe can exist without fear. The aftermath of Assassin 15 LH's discovery didn't fade like an ordinary supernova. It exploded into a legacy that continues to ripple across the field of astrophysics. From the moment it was identified, its intensity and behavior forced scientists to reconsider long-standing assumptions about the death of stars, the limits of stellar energy output, and even the diversity of cosmic cataclysms. What made Assassin 15 LH more than a transient flare in the sky was not just its mind-bending brightness, but the profound scientific questions it raised and the conversations it ignited in research labs and observatories around the world. To truly appreciate the legacy of Assassin 15 LH, one must first understand how it shattered expectations. Before its appearance, astronomers already had a growing catalog of superluminous supernovae, those rare, powerful explosions at the extreme end of the brightness scale. But Assassin 15 LH outshone them all by a wide margin. This wasn't a marginal difference, it was a quantum leap in energy output. It didn't fit neatly into the patterns and models that had been painstakingly built over decades. In fact, it illuminated the gaping blind spots in our understanding of how the universe works when pushed to its limits. Its discovery helped challenge a foundational assumption: that supernova brightness had a natural cap, governed by the physics of stellar collapse or thermonuclear detonation. Assassin 15 LH not only blew past those expected limits, it obliterated them. Astronomers were left scrambling to explain how anything could radiate with such immense power without tearing itself apart immediately or violating known laws of energy conservation. This mystery prompted a wave of theoretical papers and models exploring everything from rapidly spinning neutron stars, magnetars, to black hole interactions and entirely new categories of stellar remnants. It was a forcing function for innovation in astrophysical theory. One of the most important scientific outcomes was how Assassin 15 LH pushed the development and refinement of high-energy astrophysical models. Scientists had to rework equations, factor in extreme rotation speeds, and contemplate the interactions between magnetic fields and plasma at intensities previously unexplored. It spurred simulations that tested the edge cases of core collapse physics and mass accretion processes. Even the tools used to simulate such explosions had to be modified to account for the possibility that we were witnessing a new class of event entirely, something beyond just a more powerful version of a known phenomenon. Additionally, the sheer complexity of Assassin 15 LH's light curve, which displayed unexpected dips and resurgences, forced scientists to revisit how radiation escapes from explosive stellar environments. It invited exploration into photon diffusion models, radioactive decay paths, and the role of asymmetric explosions. Its spectral data challenged assumptions about the composition of ejecta and the thermal dynamics at play. Essentially, the event was like handing researchers a puzzle box where the pieces kept shifting, and solving one layer only revealed deeper confusion and deeper beauty. But the scientific legacy of Assassin 15 LH isn't limited to its theoretical challenges. It also galvanized the way we observe the cosmos. The coordinated follow-up efforts across a wide range of instruments, space telescopes, ground-based observatories, ultraviolet and X-ray monitors, set a new standard for rapid response to anomalous cosmic events. This multi-wavelength approach has since become more ingrained in the astrophysics community. Observatories are now more prepared to pivot resources towards sudden phenomena that don't fit traditional templates. The event also renewed interest in wide-field transient surveys like OSIS-SN. With Assassin 15LH as a showcase result, such programs received greater recognition and support. It validated the model of continuous sky monitoring, demonstrating that even small aperture telescopes, when intelligently networked and algorithmically empowered, could uncover some of the most groundbreaking phenomena in the universe. This shift helped democratize the field. No longer were only the largest telescopes capable of major discoveries. It underscored the importance of automation, machine learning, and the synergy between data science and observational astronomy. Moreover, Assassin 15LH served as a touchstone in the study of cosmic outliers, those events that don't conform, that lurk on the periphery of expectation. It became a poster child for the value of embracing anomalies, not dismissing them. The astrophysics community, traditionally cautious, began to give more weight to oddities and extremes. In doing so, the field opened itself up to a broader conception of what is possible in the life cycle of stars and the behavior of compact objects like neutron stars and black holes. Educationally, Assassin 15LH became a featured topic in university astrophysics courses and public science talks. It was used to illustrate not just the explosive power of the cosmos but also the humility required in science. Here was a brilliant example of how, even in the 21st century, the universe could surprise us with a spectacle no one predicted, something so powerful and strange that it still lacks a definitive explanation years later. It became a modern lesson in the value of curiosity, interdisciplinary thinking, and the readiness to discard old paradigms in light of new evidence. And on the philosophical front, the event reignited age-old questions about the nature of reality and our place in it. What are the limits of matter and energy? How can such violence be so beautiful, so far away, and yet so intimately tied to the atoms in our bodies, forged in stellar cores like the ones that collapsed in such events? The very existence of Assassin 15LH reminds us that we are part of a living, changing universe, one that contains wonders so intense they bend the imagination and stretch the boundary between science and poetry. Perhaps most enduring is how Assassin 15LH sparked new inquiries into the unknown. It was a cosmic flare that lit up not just the sky, but the human desire to understand. It left behind no clear answers, only deeper questions. And in that way, it became more than just a scientific event, it became a symbol. A beacon of mystery. A challenge to everything we thought we knew about stellar death and cosmic violence. Its brightness may have faded in the literal sense, but its impact continues to blaze within the community of scientists who now scan the sky with sharper eyes and broader minds. From the explosion that lit up the cosmos brighter than any before it, Assassin 15LH didn't just give astronomers a moment of awe, it gave them a textbook's worth of revelations, paradoxes, and challenges that continue to ripple across astrophysical research. What we've learned from Assassin 15LH can be categorized into two main threads: concrete takeaways that have enhanced our understanding of cosmic phenomena, and enduring questions that resist easy answers, pulling us deeper into the unknown. First and foremost, we've learned that the universe still holds surprises that completely upend our models. Before Assassin 15LH, superluminous supernovae were already considered rare and exotic, but Assassin 15LH made them look almost tame by comparison. This discovery redefined the upper boundary of known cosmic luminosity. Its energy output, over 570 billion times brighter than our Sun, didn't just make headlines, it made us reconsider the mechanisms behind the most powerful explosions in the universe. It taught us that the scale of stellar cataclysms might be more diverse and extreme than we imagined. We've also learned that classification systems are not infallible. Initially identified as a Type I superluminous supernova, Assassin 15LH seemed to fit into a category, until it didn't. As data poured in, discrepancies emerged between its light curve, spectral signatures, and the characteristics typically observed in such events. This forced astronomers to acknowledge a key limitation in astrophysics: that nature doesn't always fit neatly into our labeled boxes. The case of Assassin 15LH demonstrated how our categories, though useful, are sometimes inadequate when faced with nature's true complexity. Equally significant is what the event revealed about observational astronomy itself. Assassin 15LH was discovered by the All-Sky Automated Survey for Supernovae, ASSN, a network of relatively modest telescopes. This reinforced the critical role of automated, continuous sky surveys in modern astrophysics. It's no longer just about having the biggest telescope, it's about having the smartest system for scanning the heavens. The discovery confirmed the value of building a global, distributed system that can catch rare, fleeting phenomena no matter where or when they occur. From a technical perspective, we've gained important insights into the behaviors of light curves and spectral evolution. Assassin 15LH didn't just peak in brightness and fade away, it exhibited an unusual pattern where its light dipped and then rose again. That unexpected rise reawakened interest in delayed energy input models, such as those involving fallback accretion or Magnetar spin-down with complex energy injection phases. Its spectrum also lacked the hydrogen and helium lines typically expected in many types of stellar explosions, leaving scientists to explore unusual compositions or even speculate whether exotic materials or unknown physical processes might be at play. We've also been reminded of the importance of multiwavelength observations. To fully understand Assassin 15LH, astronomers employed a suite of telescopes covering the electromagnetic spectrum, from optical to ultraviolet to X-ray. This reinforced the idea that to grasp the nature of any cosmic anomaly, one must look at it through as many lenses as possible. No single instrument could capture the full story, but together, they painted a richer, if still puzzling, picture. This has influenced how future transient events are studied, promoting more collaborative, real-time sharing of data between observatories and institutions. However, for all that we've learned, Assassin 15LH remains shrouded in mystery. One of the most profound lingering questions is the source of its energy. Neither the Magnetar model nor the black hole tidal disruption event hypothesis has offered a complete, satisfying explanation. The Magnetar idea, while appealing in its elegance, requires a neutron star spinning at implausible speeds with magnetic fields of unprecedented strength. On the other hand, the black hole theory raises its own problems, especially since the event occurred in a quiescent galaxy that doesn't resemble the active galactic nuclei typically associated with tidal disruption events. This brings us to another lingering mystery, the nature of the host galaxy. Assassin 15LH occurred in a large, old galaxy with low star formation rates, a very odd setting for such a young, energetic event. Most superluminous supernovae are found in smaller, star-forming dwarf galaxies, where massive stars are actively being born and dying. The location of Assassin 15LH breaks that mold, leading to speculation that we may be missing something fundamental about where and how these types of cosmic outbursts can originate. There are also questions about its longevity. Assassin 15LH's light curve remained unusually bright for months, longer than expected for most supernovae, even the superluminous kind. This implies either a prolonged energy source or a unique mechanism that sustained the brightness. But without precise knowledge of the power source, we can only speculate. Another key lesson is that singular events can have outsized influence. Assassin 15LH is not just one of many, it's an extreme outlier. And yet, its impact has been immense. It sparked dozens of papers, debates, and even funding proposals centered around re-examining what we thought we knew. It has pushed astrophysics into a space where imagination and theory must work in tandem, because the observational data alone cannot yet provide closure. Its legacy also stretches into education and public understanding of science. Assassin 15LH has become a poster child for the mysterious and the powerful, proof that the cosmos still harbors events we don't understand. It brings excitement, a sense of wonder, and a reminder that even with all our satellites, telescopes, and simulations, the universe is still a wild place full of surprises. It has helped engage a new generation of students, researchers, and amateur astronomers who see in it the thrill of exploration. Finally, we must not forget the emotional and philosophical dimension. Assassin 15LH challenges our sense of cosmic proportion. When we say something is 570 billion times brighter than the sun, we are invoking numbers that strain the mind. It makes us feel small, but also deeply connected to a universe that is alive with dynamism and unpredictability. It reminds us that while the universe may appear static on human timescales, it is in constant flux, and sometimes, that flux includes events so massive and powerful they light up the sky across billions of light years. So, what have we truly learned from Assassin 15LH? We've learned that the universe is more powerful, strange, and complex than we assumed. We've learned that old models can be overturned in a single night. We've learned the value of collaborative observation, of asking deeper questions, and of not taking our theoretical frameworks as final. But most of all, we've learned that in the grand theater of the cosmos, even the brightest light can leave behind the deepest shadows of mystery. As the mystery of Assassin 15LH deepens with every analysis, one tantalizing possibility has increasingly emerged from the chaos: that this extraordinary event might not belong to any known category of cosmic phenomena, not a superluminous supernova, not a tidal disruption event, and not the product of any theoretical astrophysical model we've previously proposed. It might be something entirely new. The idea that Assassin 15LH could represent a new class of cosmic explosions is not a conclusion drawn lightly. Astronomers are generally cautious in asserting novelty in a universe that so often surprises them. But sometimes, a phenomenon appears that is so incompatible with existing categories that shoehorning it into an established box becomes more of an intellectual contortion than a scientific explanation. Assassin 15LH is that kind of anomaly. Consider this: in nearly every theoretical model applied so far, whether it be Magnetars, massive black hole disruptions, or exotic binary star scenarios, there has always been a sticking point. A contradiction. A value that's too extreme. A behavior that's never been seen before. These inconsistencies aren't just minor deviations. They are foundational flaws that challenge the viability of these explanations. The brightness is too high. The host galaxy is too passive. The light curve too erratic. The spectral signatures are too strange. So if it's not just an outlier within an existing class, what could it be? That question opens the door to a realm of exciting, and sometimes speculative, possibilities. One potential explanation is that Assassin 15LH might represent a class of hyperluminous transients, a term that, while informal, has been gaining traction. These are theoretical events that release energy on an entirely different scale than known supernovae, perhaps linked to processes in the early universe that still occur occasionally in rare environments. They might involve exotic physics, such as the decay of hypothetical particles, or even mechanisms involving dark energy or vacuum instability under extreme conditions. Another intriguing idea is that Assassin 15LH may be the result of an entirely new kind of stellar remnant, not a neutron star, not a black hole, but something in between or beyond. Some physicists have speculated about the possibility of quark stars, or preon stars, exotic compact objects made of particles even more fundamental than quarks. These objects are purely theoretical at this point, but in extreme conditions such as core collapse in massive stars, the laws of physics might permit their formation. If such an object briefly formed and then collapsed further or interacted with surrounding matter in an unknown way, it might generate a one-of-a-kind light signature. Additionally, there is speculation that Assassin 15LH could be the visible signature of a quantum gravitational event. Though this ventures into very speculative territory, some theories suggest that black holes and other dense objects may exhibit behavior governed by quantum gravity, a regime we do not yet understand. Could Assassin 15LH be the first observable indication of such a phenomenon? It's a stretch, but not out of the question in a universe where 95% of its composition, dark matter and dark energy, is still poorly understood. Others have wondered whether Assassin 15LH could be a unique merger event involving types of stars or stellar remnants never before observed in collision. While we are familiar with neutron star mergers, thanks to events like GW 170817, and black hole mergers via gravitational waves. What happens when more exotic combinations occur? A merger between a neutron star and a magnetar? A failed merger that only partially ejects material before recollapsing? The universe might allow such rare events, and they could produce energy curves and brightness levels that fall outside anything in our supernova catalogs. Of course, there's also the tantalizing possibility that we're looking at a completely new category of cosmic outburst that has only now been caught thanks to the increasing sensitivity of our instruments. In this view, Assassin 15LH is not unique. It's simply the first well-documented member of a class of events that will only become more familiar as our surveys become more comprehensive. If that's the case, we're standing on the edge of a new observational frontier, similar to the era when gamma-ray bursts were first discovered and puzzled astronomers for years before the models caught up. If Assassin 15LH is the first of its kind, the implications are vast. It would mean our understanding of stellar death and high-energy astrophysical phenomena is not just incomplete but fundamentally lacking in key areas. It would prompt a reassessment of the end-of-life pathways of massive stars, of the energy reservoirs possible in collapsed stellar cores, and of the interactions between radiation and matter under extreme conditions. It would also raise questions about the frequency of such events and their role in cosmic evolution, how they might influence galactic formation, seed black holes, or even contribute to cosmic reionization in the early universe if they occurred more commonly in the past. Moreover, if this is something new, it could mean we've opened a new window into the behavior of matter under the most extreme pressures and temperatures nature can produce. That kind of knowledge isn't just academic, it informs everything from nuclear physics to the boundaries of general relativity. And it reshapes how we design telescopes, direct observational resources, and train the next generation of astrophysicists. Of course, there are dangers in speculating too far without sufficient data. The universe has a way of humbling even the most imaginative thinkers. But caution shouldn't be confused with rigidity. Science progresses by questioning assumptions and exploring ideas that might at first seem wild. Assassin 15LH reminds us that the cosmos is not bound by what we've already discovered. It is a living, evolving frontier. Perhaps most compelling of all is the philosophical implication that the universe still holds secrets vast and strange, and that even with all our models, simulations, and sky surveys, we are still merely scratching the surface. In a time when it can feel like science has explained most of the cosmos, events like Assassin 15LH jolt us awake. They whisper of unknown mechanisms, unseen forces, and laws of physics we've yet to formulate. It may not just be the brightest explosion we've ever witnessed, it might be a flare from the edge of human understanding, beckoning us toward a greater truth. And so Assassin 15LH remains, despite years of analysis, dozens of papers, and countless late-night debates, the brightest mystery in the universe. The sheer magnitude of its brilliance is only part of the enigma. It's the context, the contradictions, and the stubborn resistance to categorization that make this cosmic event such a compelling puzzle. In the ever-evolving story of astrophysics, Assassin 15LH is a vivid reminder that not all mysteries are destined to be quickly unraveled. Some, like this one, refuse to yield easy answers, instead inviting generations of scientists to keep questioning, keep observing, and keep wondering. Its discovery was not just a stroke of technological luck, it was the result of a world rapidly gaining eyes in every corner of the sky. Instruments like those of the OSIS-SN project, space telescopes like Swift and Hubble, and an increasingly global network of ground-based observatories have ushered in a new era where rare cosmic phenomena no longer slip past unnoticed. But Assassin 15LH showed us that more data does not always mean more clarity. Sometimes, more data simply deepens the mystery. The questions that remain are not trivial ones. What could release that much energy without tearing apart the very physics we rely on to understand the universe? Why did it occur in a passive, non-star-forming galaxy? What could explain the unusual double-humped light curve, the spectral irregularities, and the odd absence of signatures that normally accompany known stellar explosions? These questions are not loose ends, they are gaps in our cosmic blueprint. As with all great mysteries in science, Assassin 15LH has had the paradoxical effect of both advancing knowledge and revealing its limits. It has already reshaped how astronomers classify supernovae, encouraged deeper inquiry into the rare class of tidal disruption events, and pushed the boundaries of what we think is possible from Magnetar engines. But more than that, it has inspired a reevaluation of assumptions about how stars die, how energy is transferred in extreme conditions, and what rare and violent forces might still be hiding in the dark corners of the cosmos. Looking forward, what might help us finally solve the mystery? For one, the future holds more sensitive and frequent surveys of the sky. Upcoming telescopes like the Vera C. Rubin Observatory, with its legacy survey of space and time, LSST, will scan the sky every few nights and generate an enormous trove of transient data. With its unprecedented ability to detect short-lived, high-energy events across a broad portion of the sky, it's possible that the next Assassin 15LH, or a dozen like it, will be detected in the coming decade. Additionally, advances in spectroscopy and real-time data analysis will allow scientists to more quickly assess the chemical and energetic makeup of these transients. Perhaps if another event like Assassin 15LH is spotted early enough, it can be studied from the very beginning, capturing light curves and spectral data that may have been missed the first time around. Moreover, there's potential in gravitational wave astronomy. Though Assassin 15LH didn't produce detectable gravitational waves, or at least, none that were identified, the continued growth of detectors like LIGO, Virgo, and CAGRA might one day pick up signals from similar events. If that ever happens, it could revolutionize our understanding of what kind of mass movements underlie these incredible displays of energy. There is also the tantalizing possibility that Assassin 15LH will become a case study for other disciplines. Particle physicists and theoretical cosmologists might find in it a reason to revisit theories on vacuum instability, dark energy interactions, or undiscovered states of matter. Even if Assassin 15LH isn't a direct observation of such exotic physics, it could be a clue pointing us in their direction. But perhaps the greatest legacy of Assassin 15LH is not the answers it gives, but the questions it dares us to ask. It is a reminder that the universe is far more dynamic, violent, and surprising than we often imagine. That in the quiet, empty corners of space, far from the bright arms of spiral galaxies or the infernos of starbirth, there can suddenly appear a blinding explosion so powerful it rivals the entire output of a galaxy, then vanishes again into silence. If we could somehow rewind the universe and replay its evolution from the beginning, how many other Assassin 15LH-like events would we see? Were they more common in the early universe? Are they signs of processes that shaped galaxies, seeded black holes, or influenced the structure of the cosmos itself? The true nature of Assassin 15LH may not be known in our lifetime. It may require a new generation of instruments, or a new generation of thinkers unburdened by the current models and open to entirely new ideas. But that's the beauty of science. Even unsolved mysteries are progress, because they tell us where to look next. So we are left with this colossal flare of brilliance, catalogued and studied but still unexplained. Like a cosmic question mark stitched into the fabric of space-time, Assassin 15LH burns into the memory of modern astronomy as more than just a supernova. It is a symbol. A symbol of wonder. A symbol of humility. A symbol of how far we've come and how much farther we still have to go. It is the brightest mystery in the known universe. And it may just be the beginning. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.